can be done on some semiconductors such as two-dimensional materials, the materials with reduced dimensionality, and we will also see what those are. And we have to do those experiments using magnetic fields and using light. Therefore, we have to understand some basics of these things, which are essentially experiments or semiconductors or magnetic fields or light. And as we progress, we will try to recapitulate all of the basics that we need for this lecture, and we move on towards more advanced stuff, which is about the latest research also, which is taking place in these materials in the world. But before coming to that, I will focus on the basics. Maybe first half of the lectures will be on the basics only. Okay, Dr. Kumar has introduced me quite well, so I do not have to go through this slide. I was a master and PhD at TIFA, then I was at France, then I was in Germany, and now I am in IISER Pune. This is my research group at IISER Pune at the moment. I joined here in 2021, so it's a rather newish group. This is a picture which is like 1 year old. So we have 6 PhD students, 3 postdoctoral researchers. We have master students, 4 bachelor master students, and we work on investigating these two-dimensional quasi-particles in magnetic field. By that, what I mean is these quasi-particles which I am talking about is, these are Coulomb-bound electron-hole pairs, which are essentially similar to artificial hydrogen atoms and also called excitons, or tryons, which are essentially 3 particles bound states now. So these are essentially, for example, 2 electrons and 1 hole, or 2 holes, 1 electron. Similarly, there could be other such Coulomb-bound species, such as 4 particle species, which is called a bi-exciton, 5 particle species, such as a charged bi-exciton. So all these quantum mechanics of these atom-like species, what happens to these in 2 dimensions when we apply magnetic field? So 2 dimensions meaning we create these particles in a 2-dimensional material. The material is shown in the background as a cartoon. So such 2-dimensional materials, which are just single layered thick materials, which are just 100,000 times thinner than your hair thickness. These are also called layered materials. So one can remove layer from one by one layer from these materials using some methods which are very popular now, called exfoliation methods. And once you produce these particles in 2D, then we study their physics in 2D by applying magnetic field and light. We've studied various effects, which I am naming some of them here, called Zeeman splitting. We are aware of that. Then there are some more effects such as valley polarization, valley coherence. I will come to some of these. Something called diamagnetic shifts, and so on, Landau level formation or Landau quantization, and so on. So if you are curious to understand this area of research, I mean what's happening in this, until 2021 I had written this invited perspective from the Journal of Applied Physics called Magneto-Optics of Layered Two-Dimensional Semiconductors and Heterostructures, Progress and Prospects. So there are various spectroscopy techniques which we use. Now this lecture is going to be much more inclined towards experimental sciences because I am a condensed matter experimentalist and that is my expertise. And I will discuss various experiments with you. For example, photoluminescence or reflectance spectroscopy, transmittance spectroscopy, absorption spectroscopy, Raman spectroscopy, something called ellipsometry, or Faraday rotation spectroscopy, Kerr rotation or Kerr effect spectroscopy, and so on. So these are called optical or magneto-optical spectroscopy techniques. And now, since these materials are so small in dimensions, literally, that we need actually focused light, essentially we have to probe regions of the micron sizes. Therefore, I have put this micro in front of all these spectroscopy. So that micro means that we are going to explore these materials on micron scales. And then we can change temperatures from 3 Kelvin until 350 Kelvin using various cryogenic methods. And we also change magnetic fields in our lab in going from 0 to 1.8 Tesla at our lab in India. In principle, we can go to much larger fields. We have collaborations in France, in Grenoble, or in Nijmegen in Holland. So their magnetic fields up to 30 Tesla are available. Those are very large facilities, and I will also talk to you about them. Because to the students, it's always exciting to tell like what the world is up to in terms of experimental sciences and what are the state of the art. So we will also discuss that. Okay. So now let's come to the fundamental concepts first in terms of experiments on semiconductors using magnetic fields and light. So first let's talk of experiments. Well, experiments are very important in science. This is a scientific method which is a well-known method that first we make some observations and then we ask some question about those observations, and then to understand that we formulate some hypothesis. Now this hypothesis does not stand there until until we predict something using it, and then we have to test those predictions. So essentially we develop some testable predictions and we have to test that. Now for testing that we set an experiment. Essentially experimental science is a central part to the scientific method. Now, we set this experiment to test those predictions. Suppose the experimental results are in line with the predictions, then it's fine. Then you can develop general theories, but otherwise one refines the experiment or the hypothesis, or alter or expand or reject the hypothesis altogether, and then make a new hypothesis and make new testable predictions, and this circle goes on until some general theories are developed, and this is the scientific method. Now, Richard Feynman used to say that it doesn't matter how beautiful your theory is, it doesn't matter how smart you are. If it doesn't agree with the experiment, it's wrong. Essentially, experimental science is very, very integral to the progress of science itself. That's what Richard Feynman wanted to say, although he was a theoretical physicist, a very well-known theoretical physicist, but had a huge respect for experimental sciences. Now, sometimes it so happens that theory arrives before experiment. For example, for lasers, Albert Einstein was writing equations of laser in 1916, just for fun. I mean, he was someone who just liked to think things out, and then he would be writing some equations and like to see, okay, what comes out of those equations. Now, he did not realize that what's coming out of this really, his equations will essentially revolutionize the world in the end, because now we know that lasers are everywhere. I mean, we would not be having this lecture if there were no lasers, because in optical communications, the optical fibers carry these signals through internet, and these signals are taken by the lasers with them. So lasers are integral to the world. In medicine, everywhere we have lasers. And I mean, wherever we think about these days in technologies, we have lasers. So this experiment arrived in 1960, although the theory arrived in 1916. Similarly, say there are more important, interesting examples such as Higgs boson. The theory was developed around 1960s, but the experiment, as all of us know, arrived in 2012. Similarly, gravitational wave, again Einstein, the theory was in 1916, but experiment arrived 100 years later into 2015, for which there was Nobel Prize. It happens the other way also in science. For example, atoms. Now, the experiment had already been performed, which had shown something that there should be something which no one realized what it should be. Okay, what I mean is the following. So the experiment was due to Robert Brown, which was on Brownian motion, and the experiment was done in 1927, where he saw jiggling of certain particles in some liquid, and this jiggling of the particles was proven by Einstein that it has to be due to atoms. Therefore, the Einstein's theory in 1905 proved once and for all that there have to be atoms. So the theory arrived later. Similarly, superconductivity experiment, H. Comerling Onnes. The experiment was in 1911, but the theory arrived in BCS theory in 1957. We all know this. Similarly, Faraday effect, for which this lecture also, today's lecture also is going to be important. The Faraday effect said, Michael Faraday said that when I am passing light through some material in the presence of magnetic field, the polarization of light rotates. Now, that means that light has some sort of magnetic or electric components that it interacts with the magnetic fields in the material, which means that this effect was seen experimentally in 1845 But the theory, which was a theory of electromagnetism, arrived in 1865 onwards due to James Clerk Maxwell, right? So therefore, theory and experiment both can come one after the other. That is what we learn from the history of science. Let's talk about light. I will only discuss a little bit about light. Light possesses a dual nature. We know that light has electric and magnetic fields, vectors which are oscillating perpendicular to each other, and this disturbance, this collective disturbance goes in the space at the speed of light. This is what James Clerk Maxwell told us around 1865 or 1866. But Einstein again came later around 1905, where he told that actually some of the experiments cannot be explained by the wave nature of light, meaning if you shine light on certain materials, certain metals, you can inject electrons from the metals. And if we think about wave theory, that the light's energy is delocalized over a large region, then this delocalized energy cannot emit these particles unless we wait for a month or something. Well, that is not photoelectric effect, it's almost instantaneous. So Einstein formulated the hypothesis that this light also has some localized particles called photons. Essentially, the photon nature was again predicted by Einstein. So for this he received no photoelectric effect. Well, for this lecture, the takeaway is that the light has electric and magnetic field components, therefore it can interact with electric and magnetic fields as well. Third, let's talk a little bit about semiconductors. Okay, semiconductors are hearts and brains of modern technology, which I have written in the title of this slide. What I mean is that if we do not have semiconductors, we would not have any computers around, we could not have any smartphones around, we could not have any efficient electronics around, such as these LED lights and such as these lasers and so on. Therefore, it's important to talk about this when we are talking about anything quantum, because whatever is happening in this semiconductor is the quantum jumps, where the electron is being taken from a valence band to the conduction band through certain means. Now, semiconductors essentially are those materials which possess intermediate conductivity between insulators and metals. But the most important part is not only that they have intermediate conductivity, but this conductivity can be controlled by doping, by electric field, by light, and by various such means. Now, once this control was achieved in semiconductors, we have had our joy of creating lots of devices such as transistors, such as then lots of transistors are put together and computers are created, and such as these photovoltaics and whatnot. Everything. It's all because we can control the conductivity of the semiconductors. For example, silicon, the most popular semiconductor without which the world does not run. It's extracted from sand, from SiO2, using various methods, and then processors of computers and smartphones are created with silicon. Similarly, photodetectors and photovoltaics such as these solar cell panels and so on are created with silicon and are commercialized at a level where we cannot imagine today. Therefore, the world is highly dependent on semiconductors. There are more examples such as gallium arsenide. Now, this is a semiconductor which has been used in the lasers in CD and DVD drives. Now, of course, CD, DVD drives are sort of obsolete these days, but this has played an important role. Similarly, in the red laser pointers or in optical fiber-based communication, such as internet, gallium arsenide has a very large role to play because it's used for creating photodetectors as well as lasers for creating modulated beams in the optical fiber-based communication. All the LEDs that we see around today, which are essentially blue, green, and red LEDs, or white LEDs, which are the combination of these three, blue, green, and red, are based on gallium nitride. Now, this semiconductor, which has been a mystery since for very long on the way how to dope it and on the way how to create pure crystals of this and so on. But this has evolutionized the lighting world, what we have today, and also the lasers are created with this. And we know the story of Shuji Nakamura. Maybe if you are interested, please read the story of Shuji Nakamura, who received a Nobel Prize for creating gallium nitride. Okay, then indium phosphide, another semiconductor which is very, very important for optical fiber-based communications and for red laser pointers. Therefore, all these semiconductors, I am giving you only few examples, are the ones which are very important for the world in which we live in. Now, we are physicists, so we have to understand physics behind the semiconductors. And when I say physics behind semiconductors, what we have to do is, what we have to understand is the band structure. Now, this band, the topic of band structure becomes very important or in the beginning of the solid state physics courses which we teach, where it starts with the fact that once we place an electron in a periodic crystal, the electron loses its own identity but becomes a part of the whole crystal and is now it's called a quasi-particle which has some effective mass m star. Essentially, you apply electric field and you check its motion, and the motion is now dictated by a different mass m star, and it's also called block electron. Essentially, the electron is behaving as a wave which is a part of this periodic potential of atoms. That's called a block electron. But the question is how the bands are created. Well, suppose we have an isolated atom. Suppose I have an isolated silicon atom. Then I have 4 electrons here in the outermost shell. In the 3s and 3p, there are 2 each. And once I want to bring all of these atoms together and make a crystal out of it, what happens is that as I am reducing the interatomic spacing and as I am bringing all these atoms together and making a crystal out of this by putting lots and lots of atoms like 10 to the power 22 to 10 to the power 23 atoms together per centimeter cube of the crystal, then the outermost shells or the outermost orbitals, they start to hybridize with each other. Why? Because the Pauli's exclusion principle tells us that no 2 electrons can have the same state. As simple as that. Now, since they cannot have the same state, but they belong to the same 3s or 3p orbitals, but they are brought together, then their orbitals start to overlap. These orbitals cannot now overlap in such a way that they have the same energies, because now the states have to differ, because now they are occupying the same physical positions. Therefore, their energies of these nearby lying electrons in these all these atoms, they start to split a bit or differ a bit in energy. Therefore, a band starts to create. So lots and lots of energy levels start to create due to this hybridization, or also called Pauli repulsion. We reduce the energy spacing and then we come to the actual interatomic spacing. By actual, what I mean is the crystal is stable for this interatomic spacing A. And once the crystal achieves this interatomic spacing and it's stable, that at that point what happens is we have these 2 bands, and these 2 bands are formed in such a way that the valence band's states, all the states are completely filled of electrons, because we had 4 electrons here and 4 electrons were empty. Therefore 4 n states are filled here and 4 n states are empty here, meaning the conduction band is completely empty only if we talk about 0 Kelvin temperature. So the conduction band will be completely empty and valence band will be full, because there are no more electrons available. But if I raise temperature a little bit, then what would happen is some of the valence band electrons, due to Fermi-Dirac redistribution, at the tail of the distribution, some of these electrons will acquire sufficient energy to go to the conduction band, and this semiconductor will start to conduct. At the moment at 0 Kelvin, it's an insulator, but it starts to conduct as soon as you give it some temperature. Only a few electrons, of course, will go to conduction band if the temperature is very low, but as the temperature is increasing, more and more electrons occupy the conduction band because of just the thermal agitation or the thermal energy, which is on the tail of this Fermi-Dirac distribution function, which is a step-like function. Okay, typically this band gap, the gap between the conduction and valence band, this is from far infrared, near infrared, like 0.3 electron volt, to UV, ultraviolet light, like 3 electron volt in semiconductor. That's the typical, these are the typical numbers. But if we have to understand this band structure better, what we draw is something called an EK diagram, where the y-axis is energy and x-axis is the crystal momentum, where it's found that the conduction and valence bands in this EK diagram are parabolic. Now, this is the band gap. This is a parabola. This is looking like an inverted parabola, but this is a real, but this is also a actual parabola because this belongs to different charges. I mean, here the charges which are responsible for conduction are holes in valence band, and the charges which are responsible for conduction in the conduction band are electrons. And it turns out that the mass of the charges, the effective mass m star which we had talked about, the mass of the charges in this bands is given as the inverse of the curvature of these bands. So take the second derivative, take an inverse, multiply it by h cross square, and you get the mass. So essentially the effective mass of the charge carriers can be easily determined if the band structure is known or the EK diagram is known. Now, semiconductors historically have been very important for studying fundamental physics. For example, this first chapter of our quantum mechanics textbooks, which is about a particle in a box. This is a nice theoretical concept. It has been a very nice concept when the quantum mechanics started, but to test this concept that when you put some electron or some charge carrier inside a potential well, the energies of these charge carriers get quantized. This concept could not be tested for many decades in laboratory. The reason is that in the potential well here, the potential well that we discuss in our quantum mechanics textbooks, this L, the length L, which is the thickness of this potential well, this is of the order of de Broglie wavelength of the electrons or de Broglie wavelength of the charge carriers in the material in which the carriers are residing. For example, if I think of a semiconductor, the de Broglie wavelength of electron in this semiconductor called gallium arsenide, which is very popular, is of the order of 30 nanometers. Now the problem is that creation of such thin layers of the material, or 15 nanometers, creation of such thin layers of the materials which are very pure was very difficult task in the laboratory. One can think about it in the following way, that the thickness of our hair is of the order of 70 microns. But what we need is something of the order of which is 7 nanometers, which is 100,000 or which is 10,000 times thinner than the hair thickness. Essentially, you have to put 10,000 layers of this material on the top of each other, and then you get something like which is thick like a hair. So that has been a challenge technologically to create such a quantum well. So before that, before this semiconductor era, when people were not able to create these quantum wells, what people were doing was that they would check some atom. For example, this is 1 by r potential of an atom, and then there would be these quantized state, and they would calculate these quantized states, and they would approximate this with the well. Now, of course, this is not really a well. This is a very bad approximation. It does not give answers close to the quantum well approximation here. Therefore, the concepts were not able to be tested until 1970s, when the particle in a box was actually created artificially, essentially, which was called a two-dimensional quantum well. And how it was created is the following. Suppose I create some methods in the laboratory which are able to give me very thin layers, and these methods are also called epitaxial methods. There are various methods. One is called molecular beam epitaxy, one is called metal organic chemical vapor deposition, one is CVD, and so on, chemical vapor deposition. All these methods can be used to create something like a quantum well. Now, on the x-axis, I am showing the space. Essentially, there is some material like gallium arsenide, which is sandwiched between the two different materials. There are two barriers of different material called aluminium gallium arsenide. Now, why do we do that is the following. Gallium arsenide, first of all, has this well width, or the width is only 10 nanometer, which is of the order of the de Broglie wavelength, which means that the quantum effect should be active in this. But They will only be active if there are potential barriers around, because we have to create this potential barrier, and this potential barrier can be created with a wider band gap material. Meaning, if gallium arsenide has this conduction band and this valence band, then I need some material which has a conduction band higher than this, which is on the both sides, so that I have this well. Similarly, I have a valence band. Now this is an inverted well. It looks like a barrier, but it's actually a well because the holes reside in the valence band. Therefore, the material aluminum gallium arsenide, which has this valence band, which is deeper compared to the valence band of gallium arsenide, also creates a barrier for holes. So essentially, electrons are quantized in this and holes would be quantized in this. How do we check this? Well, what we can do is we can imagine that there are these states now which are quantized, and how do we test those states? We have to push some carriers from this valence band to the conduction band. How do we push this? We shine photons. We make optical transitions. Once we make a photon of this energy, we take an electron from this place to this place, and then a hole is created in this place. Then we have an optical transition, and this optical transition, because the photon is responsible for creating this optical transition, the photon is absorbed. Therefore, if I just check the intensity of the photons which are coming out of the material for certain energy which is in resonance with this energy, with these energies, for example, there are two transitions with these two energies, then the number of photons appearing out of the material for these two energies will be much lesser compared to the other wavelengths or the other energies, which means the photons corresponding to these energies are absorbed and the optical transition has taken place. Now, looking at the energies of these photons and calculating with our particle in a box model, we can calculate if that energy has fitted in well with that, and that has been fitting in well for a very long time. We have not found many deviations, and the theories of quantum mechanics are fine. And this is how all of this was tested. Now, similarly, semiconductors have played an important role in studying something else called excitons. Okay. Essentially, one can create artificial hydrogen atoms again in the material and study the quantum mechanics of hydrogen atoms. Now, the thing is the following. To study the quantum mechanics of hydrogen atoms, we have in quantum mechanics, we have written lots and lots of theories where what is happening is the following, that if I have a hydrogen atom, if I apply magnetic field to this and I apply magnetic field term in the Hamiltonian, or if I apply electric field term in the Hamiltonian, what is going to happen in this hydrogen atom to the states of hydrogen atom, the 1s, 2s, 3s, 4s, and so on, all these states? That is the question. Now, many times it so happens that the magnetic fields that are available in the laboratories to perturb these hydrogen atoms are not enough. For example, if I'm talking about the binding energy of the hydrogen atom, I know that this is 13.6 electron volts, a well-known number. Now, this 13.6 electron volts is such a large binding energy that if I have to overcome this binding energy by applying some magnetic energy from outside, then I will need a magnetic field which is of the order of 100,000 Tesla or something. Now, such large magnetic fields like 100,000 Tesla to perturb a hydrogen atom and to test our theories are not available on Earth. It's not possible to have this magnetic fields available on Earth. These such magnetic fields are only available in celestial bodies such as neutron stars. But neutron stars are made of neutrons. There are no hydrogen atoms in the neutrons. So in the end, anyway, we cannot test the theories or quantum mechanical theories for hydrogen atoms under magnetic fields. Now, this is such a basic question. This also becomes a part of our textbooks. Then, what is the way out? Well, the way out is the following. If we are able to create these hydrogen atom-like species in certain material, then it turns out that within the material, the binding energy of the hydrogen atom is reduced. It's screened due to the dielectric function of the material. How much it's reduced? It reduced many orders of magnitude, even 4 orders of magnitude. And so therefore from 13.6 electron volts, we come to like just milli electron volts. Therefore, the magnetic fields that are also needed for this perturbation come down by a factor of 10 raised power 4 or something. Therefore, in laboratories now, in the solids, we can create a gas like that of a hydrogen atom by shining lots and lots of photons. And then We can apply magnetic fields and study what is happening to that gas and check with our theories. Now, how do we create this gas? The point is, shine photons, again, electron and hole pairs are created because an electron is pushed from valence band to conduction band. These electron hole pairs are bound by the Coulomb interaction for some time now. Since it is bound by Coulomb interaction, well, guess what? It's similar to a hydrogen atom. There is a positive charge and a negative charge. This is bound, and we can study the physics of hydrogen atom. Not only that, if we think about a two-dimensional material, here I have given a picture of a two-dimensional material, then this hydrogen atom is actually a two-dimensional hydrogen atom if we create it in this two-dimensional material, which means that now we can study two-dimensional hydrogen atom physics as well, which is otherwise impossible for atomic physicists. They cannot create two-dimensional hydrogen atom, whereas solid-state physicists can create two-dimensional hydrogen atoms and study their physics. Moreover, place an electron in a solid such as a semiconductor and apply magnetic field. What we notice is there is something called Landau quantization, where the electrons get quantized, their energy gets quantized, meaning they start to, if one thinks semi-classically, they start to rotate in cyclotron orbits at their own location. That means their motion is quantized and their energy levels are quantized quantum mechanically. The energy levels of these electrons, of this electron gas, which when we apply perpendicular magnetic field to this electron gas in a solid, is given as a quantum number n here. So n minus half h cross omega, where omega is a cyclotron frequency EB by m star. So all these things have been studied very, very regularly by using semiconductors as a platform. I have already talked to you about hydrogen atoms in magnetic fields, where atomic hydrogen is impossible to study because very large fields are needed, whereas excitons require 10 Tesla or below because the energy, Coulomb energy is screened of these excitons, and therefore such fields are available in the laboratory to study quantum mechanics of hydrogen atoms in the laboratories. Okay, now I have been talking to you mostly about these quantum wells, which have been very important for fundamental physics such as 2D hydrogen atoms and so on. But these quantum wells actually have been technologically so important that for creating efficient light sources such as LEDs or solid state lasers or photodetectors, that those revolutions would not have been possible without these quantum wells. So essentially, not only these quantum wells have importance from the fundamental science point of view, they are also important technologically. So lots of technologically applications. But these are quantum wells and they are difficult to create in the laboratory because they need some very specialized methods. But these days, for studying physics, we have something called these two-dimensional semiconductors, as I told, which are essentially layered materials made of like molybdenum and tungsten and sulfur, selenium, tellurium, some of the atoms. And when you combine them and create compounds, the compounds are called MOS2, molybdenum disulfide, tungsten diselenide, molybdenum diselenide, tungsten diselenide, and so on. All these combinations can create these two-dimensional materials, which are layered materials, where you can remove layers from these materials one by one and place on a substrate, such as shown here, such as the silicon substrate. Of course, a very thin layer of silicon dioxide is coated on the substrate because this thin layer makes us see this very thin film. Now, this such a thin film, it's 100,000 times thinner than your hair thickness, meaning this tungsten disulfide. It's very thin, it's just 1 atom thick. How do you see it? Well, to see it, we place this on this substrate, this special substrate, and there are these interferences which take place between silicon dioxide and this film, which make the absorption in this film grow larger, and this absorption would make us see this film better. So even a single layer film is. So using these two-dimensional materials, now lots and lots of other new uh, applications and physics is being thought about. There are some things, I will not go into details, but if you are curious, you can check these keywords. There is something called valley-based physics or valleytronics, which is done lots in these two-dimensional materials, where quantum computers are being thought about to be made using these valley degrees of freedom. There are some new magnetic moment degrees of freedoms in these materials, which are very robust and which can be manipulated using electric and magnetic fields. One can create heterostructures of these materials by putting them on the top of each other because they are van der Waals materials. So we can put on the top of each other and we can make small twists between them. And it turns out that these twists are very important because these twisted heterostructures have shown us superconductivity, for example, in these materials and many other exotic phenomena. Therefore, these materials are being used for new two-dimensional physics and new technologies. And I have talked to you some of them already. Now let's come to the combination of semiconductors and light. When we combine semiconductors and light, well, we have optics on semiconductors. I already told you, shine photons, create electron hole pairs, and then this process is called optical absorption. This because the photon is absorbed, electron hole pair is created, but this electron also falls back into this hole, and then the process is called photoluminescence because the light which was absorbed by the semiconductor is now given out. The process is called photoluminescence. So optical absorption is used for many absorption based devices such as photovoltaics and photodiodes and so on, whereas photoluminescence is used for emission based devices many times. Or there is something called electroluminescence. One can push electron hole carriers in conduction and valence band using uh, using electronic means, and then one can get light out of the materials, and the process is giving rise to all the LEDs and lasers that we see around. In all these processes, the momentum has to be conserved, as we know in physics. So this is the momentum axis, the crystal momentum axis. It turns out that the photon's momentum is very small compared to this crystal momentum axis, meaning on this axis the photon's momentum will be very tiny, about 100 or about 1,000 times less than this crystal momentum axis, which means that the photon does not contribute much to the initial and final momentum of the electron, which means that the electrons which starts from this point directly goes above in the conduction band at this point, and the process is direct in nature. Direct meaning it is directly at the same K point of the material. Now such material where the band gap is direct in nature, meaning the lowest energy separation between conduction and valence band in the band structure of the material is at such same K point. Such materials are called the direct band gap materials, and they are efficient emitters of light. What I mean is the following, that if we create a lot of charge population in conduction and valence band, these charges would like to come back and join each other. And since the momentum mismatch is not there, photon has a very small momentum, all these charges from the conduction band would come back to the valence band and would give out light. And this light is efficiently emitted, and these materials such as gallium arsenide or gallium nitride are efficient emitters of light, which are these direct band gap materials. They are used for making LEDs and lasers. In certain materials, what happens is that the bottom of the lowest energy conduction band, meaning in the whole band structure in the K space, the lowest energy of the conduction band is at a different K point compared to the top of this valence band, which I am showing here in blue. And these materials are called indirect band gap materials because for emission of a photon, now you have to take care of this momentum because photon cannot provide this momentum. And what provides this momentum is also called a phonon. And this phonon is essentially a quantum of lattice vibration. We teach that in our solid state physics books. And now this becomes a two-particle process. Essentially, a phonon has to be involved in the process of emission of a photon. And once we know that there are extra particles involved and in any process, the cross-section of that process goes down drastically, meaning the process becomes inefficient. Essentially, this photon will be inefficiently emitted. Therefore, the materials such as silicon and germanium, which are indirect band gap materials, are inefficient emitters of light. They are not very efficient emitters of light, but they can still absorb light very well, because once we extend this conduction band somewhere there, then there would be these states to absorb lots of light, because the light vector will be, the light has very small momentum, therefore the transition has to be direct. So absorption is possible, but emission is not possible, because emission takes place efficiently only from the bottom of conduction band to the top of the valence band. That is not. Okay, now to measure all of these optical processes in semiconductors, we need certain setups. Well, in such a setup which we have at IISER Pune, What we need is some light source. There is this, for example, a tungsten halogen lamp light source or the xenon lamp light source. And this light source, the light from this light source follows such a path. There is a mirror here which takes this light to this path, and then it takes above, then it takes on the right. There is a beam splitter here which is not shown, but it's put there. And then this light passes through this objective lens and falls on a sample which is kept in this cryostat at 4 Kelvin. Now the thing is, why am I doing this? I have to shine light on the sample from the top and then I have to reflect light. Okay, so essentially the white light is taken, is shown on the sample from the top through this and focused through this objective lens, and then it's reflected back from the sample. Now reflected light goes back and then there is a mirror here, and then it goes to the detection stage here with a spectrometer. There is a spectrometer which is kept in the back. Now, what do we do here? We shine light from the material, reflect light off. Suppose I know the reflection of the substrate, meaning what I have done is I have a substrate and then I have put the material or the semiconductor on the top of this substrate. Suppose I know what the substrate is, because I mostly know it can be sapphire, it can be quartz or something, right? It can be silicon, piece of silicon. Then the light which is reflecting from the substrate, I already know the reflectance of the substrate, so then I exactly know how many photons I am capturing in this device, in the spectrometer, as a function of wavelengths. Therefore, I know the incident spectrum by measuring spectrum of the substrate. Therefore, as soon as I go by moving my sample using this XY stage under the light beam, that means now my sample is under the light beam, then I reflect some different amount of photons, and then I exactly would know how much photons are being reflected at different points of the wavelengths as a function of wavelength, because I already know how many photons were there at different wavelengths by measuring number of photons from the substrate. Now I check some unknown things such as my sample, such as my semiconductor, and I can measure the reflectance spectrum. This is the way reflectance spectrum is measured. Similarly, one can shine light from the bottom and one can measure the transmission spectrum. Light just shines from the bottom of this cryostat and passes through, and the transmission spectrum is measured. All right. One can also do various other things with this setup. I will not go into the details. Essentially, there are various things that can be done like photoluminescence, reflectance, transmittance. Absorption essentially is 1 minus R minus T. So there is reflection and transmission one has measured. 1 minus R minus T. Also, there can be some scattering losses, but in these crystals, the scattering losses are minimum. Therefore, there should be minus S, but we ignore that. One can do photocurrent measurements as a spot size of 1 micron and as a function of temperature. This is all that can be done using such a method. Now, I was talking about excitons. Excitons are the Coulomb-bound two-particle states. Essentially, I have shined a photon, an electron-hole pair is created. Now, this exciton, since it's a bound state of electron and hole, bound state meaning the energy is now lowered down because binding reduces energy. We know that. By an amount equal to binding energy of this exciton, the exciton resonance will appear below the electronic band gap in energy. Suppose the zero of energy is there, then Eg is the band gap. The excitonic resonance will appear below the electronic band gap by an amount equal to binding energy, meaning the actual absorption, the energy of the absorption will be reduced compared to the electronic band gap. This will be my, if I want to say, optical band gap. So exciton binding energy will be EB is Eg minus E optical. That is how one measure the excitons binding energy, by measuring electronic band gap and by measuring optical band gap and subtracting these two. Similarly, this exciton can emit light as well. By when electron and hole fuse together, they emit light. So this is essentially excitonic emission. Now I have a video, but I will not like to play this because I will not be able to transmit the sound to your video. But essentially, these excitons absorb very strongly at the resonance, which is at the optical band gap, and they also emit very strongly, almost resonantly, at the excitonic energy. Now, I have been talking all about quantum wells and two-dimensional materials. What do excitons do there? Well, here is the answer. Suppose I shine photon and I create this transition. This is the band gap of this quantum well. Because below this there were no states. I mean, before confinement there were of course lots of states in the conduction band and in the valence band. But after confinement, the first state of electron is there and the first state of hole is there, and the first excitonic or the first optical transition which is taking place is of this energy. Therefore, this is the band gap. Now, of course, I told you that electron and hole pair are bound with each other to create excitons. Therefore, the actual energy at which the transition will start taking place will be slightly low compared to the electronic energy by an amount equal to the binding energy. So this will be the optical band gap. Therefore, in two dimensions also an exciton is created. If I want to predict the spectrum of this exciton, I have to understand that this exciton is actually very similar to that of a hydrogen atom. Therefore, the absorption spectrum of these excitons will be very similar to the absorption spectrum of two-dimensional hydrogen atoms. And why two-dimensional? Because this is a two-dimensional quantum well. And the predictions are well known. The predictions say the following, that if I have a band gap Eg at certain energy, then the amount of energy below which the exciton will appear is the binding energy, and this is the optical band gap, and this exciton will appear like a very strong resonance. It's an internal resonance of the system. Therefore, in the absorption spectrum, it appears as a very strong peak. This is expectation again. This is not experiment. What is more expected is the following, that this transition is actually the ground state exciton transition, meaning like similar to hydrogen atom, there are ground state and excited states. Like there is a 1s state which is the ground state, and then there are excited states 2s, 3s, 4s, 5s and so on. And beyond the band gap there is continuum, meaning the electrons and the holes are not bound anymore, they are unbound, but still there is Coulomb potential, of course, because the electrons are still a part of the crystal, so they are scattering from the Coulomb potential of the holes, which means that these scattering processes lead to some scattering states, lots and lots of scattering states. Now this is again expectation, and where does this expectation hold true in the experiment? Well, let's zoom into this part. Ground state I have seen. I have to show you the excited states and scattering states. Now I zoom into this part. I notice this ground state is there. There is a 2s state which goes very close to the band gap. This is what is expected again, the excited state. This will have a very low intensity. In fact, the expectation is that the intensity of the nth excited state goes down as n cube, meaning the 2s state will have 8 times lesser intensity. Similarly, 3s state will have 27 times lesser intensity compared to 1s state. So this will be even small. So this is mostly hidden. Essentially, now the problem is, if we have to study these ground states and excited states all together, we have to be able to study these 2s and 3s and 4s states and so on, which we will not be able to see because they are merged with the band gap, mostly because of the line width broadening. These line widths are broadened. Also, the intensities of these states are very low. So therefore, the excited states are expected, but with very low intensity. What about the scattering states? The scattering states tell me that the theory tells me that what happens is that due to this Coulomb scattering, the effective absorption cross section rises, also called as Sommerfeld enhancement. And this cross section, which is beyond the band gap of the material, it is supposed to be a 2D, like a step-like function, because in the theory, the absorption of two dimensions is a step-like function, also called two-dimensional joint density of states, which the absorption follows. But the absorption is enhanced due to the Coulomb enhancement. So this Coulomb enhancement is expected in the experiment as well. The Coulomb enhancement says that this absorption step-like function of the two dimensions, it should look like a step, but it should also slightly fall down. It should also slightly fall down, and absorption should be enhanced. This is also called Sommerfeld enhancement factor. Let's see what happens in experiment. These experiments which I had done back in 2010 when I was doing my PhD, these experiments involved again this gallium arsenide quantum well. Now, in this quantum well, there are two types of excitons which are visible in absorption spectrum. One are called heavy hole excitons, other are called light hole exciton, meaning what happens is that there are two types of valence bands with different curvatures. I told you that curvature is related to the effective mass. Therefore, one of them has a larger effective mass, other has a smaller effective mass, a deeper curvature, and there are two types of holes which make two types of electrons with two types of excitons with the same electron in the conduction band. Now, there should be two resonances which are ground state resonances. So if we measure absorption, there is one resonance here, there is another resonance here. So these are the two resonances for the heavy hole and light hole exciton which are visible. Also, the excited states which should have been appeared here for the heavy hole and light hole excitons do not appear. As I told you, their intensity is highly quenched and also they are very close to the band gap. The thing is, their binding energy is, their line width is large and the binding energy is small. For example, this would be the total energy uh, energy interval in which all these excitons will appear, these excited states appear, but we are not able to see because this binding energy is very small as well as the line width is very large, because the line width is already of the order of binding energy. This is not nice, that's why we are not able to see. But for heavy hole and light hole there should be two steps here for Sommerfeld enhanced density of states or Sommerfeld enhanced absorption, and this step is visible. This is a combined step for both heavy hole and light hole. Therefore, what I mean is that in an experiment like this, since the exciton binding energy is pretty large, line width is also pretty large, the ground state exciton resonance is visible, whereas excited states are not visible, and as theoretically expected, the Sommerfeld enhanced density of states step is visible. Okay, I will like to stop here for now for 5 to 7 minutes. We can meet again at 3:05, I would say 3:05 p.m. What do you think, Dr. Kumar? Is this okay?
Yes, sir, it is perfectly fine.
Okay. Okay, so let's meet at 3:05 and we continue from there. By the time I am also available here, I will be waiting, and if there are any questions, I can take questions in this interval as well.
Okay, sir. I see your lecture is trending.
It's trending. Ah, you mean
Uh,
I am standing? Okay. Yeah.
yeah, you are trending.
Yeah,
That's
with
why.
that, I like to give lectures when I am standing.
Okay, okay.
Okay, so someone had written that the audio was intermittently breaking. Was it clear or there were breaks?
Possibly, maybe some issue with the participants. Your audio was clear for me all the time.
Okay, that's good to know.
Yeah, and I would like to request the participants, since Dr. Assis is available, so please mention the queries in the chat box now.
Yes, I'm
So,
happy to discuss.
yeah, I think with time we'll have some questions.
Yeah.
Meanwhile, just to request you to elaborate
Yes.
how these techniques are going to be helpful in quantum technologies.
Yes. So essentially, in this area of quantum materials and devices, the area is evolving in a certain direction which needs the materials which are very small in sizes, meaning in micron scales in the lateral dimensions. And we should be able to see all of these quantum effects taking place in these materials using optical means. Optical means are nice because you just shine light. The information, quantum information, is encoded in the light or the spectrum of the light that we are measuring. It can be the luminescence or transmittance or reflectance or Raman and so on. And just measure the spectrum and come to know about various quantum mechanical properties of the material. So essentially, all these techniques are useful for characterization of the materials without breaking the material or without destructive means. So these are not destructive techniques essentially. That's why light is nice. This is why optical techniques are nice. Similarly, if one has to learn about the magnetic moments of the material, then one has to apply magnetic fields, but still the effect is readable through light. One can do various things such as Faraday rotation, Kerr rotation, magnetopl. We will discuss about some of these as we move on. Okay, so there is a
Yeah. Please, if
question.
you can read directly, this will be nice.
Yes, so uh, Jagdish Chandra ji is asking, is it possible to deposit MOS2 using sputtering techniques? Jagdish ji, actually, I am not an expert in creating these samples. What we normally do is we just get single crystals from our collaborators of these materials. The single crystals are created using in by just fusing the materials in a furnace at a large temperature, and chemical reactions make it happen, make it possible to create single crystals. And then we exfoliate those materials in single layers. But using sputtering, I am not sure because I am not an expert, but I think in principle it should be possible. One should be able to sputter molybdenum in sulfur atmosphere, and then it should be possible under certain conditions to create these materials. Senthil is asking, is it possible to make an electron cloud artificially? If you are talking of an electron cloud within a material, well, we call it an electron sea or an electron gas, and that is definitely possible. People create them all the time. So what you do is, you dope a material very, very heavily with an N-type material. Suppose you have a piece of silicon, you dope it with phosphorus, and then you create N-type, and then you create lots of electrons which are freely available to move around, and this is an electron gas. Essentially, in the metals, what you have is an electron gas as well, because there are lots and lots of free electrons which are moving around the metal. So that's also an example of an electron gas. In two dimensions, 2D electron gases are very easily created using various methods in quantum wells by doping the materials, by doping the quantum wells with certain methods. And these 2D electron gases are very important because you have to have them for example, light emission based technologies and so on. Because you have to have electrons and hole gases, you create them with electronically, you inject electrons and holes, these carriers. Essentially, you artificially dope the materials, the p-n junctions, and then you create lots and lots of carriers which combine with each other and give out light in the forward bias. Okay. Manishi is asking, my question is slightly misplaced from the topic. Is there a difference between measurement and observation in terms of quantum? These two terms are generally used interchangeably. Manishi, yes, this question is quite different than what I am supposed to discuss here. That is true. Therefore, I would rather, at the moment, I would resist because this discussion, of course, can be made, but this discussion will go very long then because this goes towards mildly towards philosophy and mildly towards the facts. Sorry about this. Senthil is asking if electron gas cloud, how could fuse? Okay, I could not understand this question. Can you please elaborate? Thank you. Indirect band gap. What is the question? Do you want me to explain what's an indirect band gap?
Yeah, exactly. Earlier also he raised the query.
Okay, so indirect band gap is essentially a property of a material where you bring lots and lots of atoms of the material together and create a crystal out of this, and you find in the end that the material has an indirect band gap. Now, what it means is the following. When you create a crystal, there are these valence and conduction bands as we discussed in the lecture. Now, these valence and conduction bands essentially appear due to hybridization of various orbitals of the material. Now, it turns out that this hybridization can lead to certain points in the Brillouin zone. Brillouin zone meaning this is the k axis, the crystal momentum axis, and this is the energy axis. where there are different types of bands. For example, there is a valence band at certain point at this point of the Brillouin zone, but the conduction band, the bottom of the conduction band lies at some other point of the Brillouin zone. Now, these two bands are spatially or momentarily, meaning in terms of momentum space, they are separated from each other. And whenever there is a separation between the conduction and the valence band maximum and the conduction band minimum, then we find that this material is called an indirect band gap, because the band gap is not at the same point, K point, which is called the direct band gap. And to excite this indirect band gap, one has to complete the momentum as well as energy. One has to fulfill the momentum condition. And to supply this momentum, normally we use phonons, the lattice vibrations. Thank you. Manish is writing, I suppose you will allow me to write you an email later. Sure, definitely. I can write my email address here as well in the chat. Here is my email address. Please feel free to write me an email. If electron cloud is formed in the lab, is it possible to create thunder and lightning artificially? Well, this is going a slightly different direction, but yes, this is definitely possible. We should not do this. But we know that there are these plasma balls, right? You have seen these plasma balls where there is a large potential difference that is created between the ground, which is the outside surface of the plasma ball, and inside there is a small Tesla. Um, there is a small Tesla conductor or this Tesla coil, and then there is this lightning that's created between the outermost and inner electrode of this plasma ball. And this is essentially lightning. One can create this lightning essentially. Okay, so I think we are at a time where we have to start again. What do you think, Professor Kumar?
Yes, sir. We can start now.
Okay, so then I will share the screen and we will start from the same point again. Okay, so hello everyone. Welcome back to the second half of this lecture. We have talked about light in semiconductors and in quantum wells. We have talked about excitons. We have talked about excitonic resonances. We have talked about how much fundamental science and technologies are done using semiconductors and two-dimensional semiconductors. Let me proceed. Let me proceed from quantum wells to now layered semiconductors. Now, I was talking about excitons, which have a binding energy of the order of 10 milli-electron volt in these 3-5 semiconductors such as gallium arsenide. There are these recent materials which I talked about, which are layered materials such as MOS2 or MOSC2, WS2 and so on. And these materials are called transition metal dichalcogenides, TMDCs, meaning there is a transition metal like tungsten and molybdenum, and there is this chalcogen atom, dichalcogenide, so SO2 and so on. Okay, someone is writing video is not coming. Dr. Kumar, can you see my video? Okay, I'm not really sure if the video. Okay, it's coming. Okay, so then we continue. Thank you very much. So to those participants to whom the video is not visible, it should be visible soon because others are able to see it. Okay. So in transition metal dichalcogenides, the physics is similar to that of 3-5 semiconductors, but it's still very different. The reason is that in 3-5 semiconductors such as gallium arsenide, the binding energy is like 10 milli-electron volt, very small. But in transition metal dichalcogenides, the binding energy is very large, is 1 to 2 orders of magnitude larger than the 3-5 semiconductors. Now, how does it help me? It helps me in the following way. There is this 3-5 semiconductor such as gallium arsenide. Exciton has a binding energy of 10 milli-electron volt. This binding energy is much lower compared to the room temperature energy, KT. The KT scale at room temperature is just 25.8 milli-electron volt, which means that this is much larger compared to this 10 milli-electron volt, and an exciton, if created in the two-dimensional quantum well like that of gallium arsenide, will be broken at room temperature because there is lots of energy, thermal energy at room temperature for 3-5 quantum well. Whereas In transition metal arcogenide, the binding energy is much large. Therefore, for 3,5 semiconductors, we actually have to lower the temperature down to liquid heliums or at least to liquid nitrogen to start doing something. Whereas in this layered semiconductors, we do not have to do it. Even at room temperature, nice excitonic resonances are visible. So we are able to do 2D hydrogen like physics even at room temperature for these layered semiconductors. Now, here is the spectrum of this layered semiconductor. This layered semiconductor is called tungsten disulfide. I have not written it, but this is called tungsten disulfide. And there is an absorption peak which is visible here. This absorption peak is, this is coming from a single layer of the material, a layer which is 100,000 times thinner than a human hair thickness. And from this, we already noticed that this peak is very large. I mean, see, 28% or 26% of light is absorbed just from a single layer at this frequency. So this is the excitonic resonance or the ground state exciton which we discussed. Not only that, we can see excited states of the material. So there is a ground state, 2s, 3s, 4s, 5s. These are also visible easily, or the Rydberg states. The reason is that now the binding energy is so large, the particle, the electronic band gap is here, that lots of space available. Even for broadened resonances, these excited states are visible. So that is very nice. Thirdly, not only that, we have these other particles called tryons, which are essentially now three particle bound states. You have a hole, and then in the first shell, which is the 1s shell, there are two electrons, or you can have one electron and two holes. And these tryons are also visible in the absorption spectrum. So one can do H negative ion like physics in solids. In gallium arsenide, this physics is very difficult to do because binding energy is just 1 electron, milli-electron volt, and one has to do actually this physics at very low temperatures such as 4 Kelvin. Whereas in transition metal dichalcogenides, even at room temperature, these tryons are visible. Therefore, one should be able to do all this stuff at elevated temperatures or at room temperature. So the life is easier in terms of temperature. But it's difficult because now the sample sizes are very small. The sample sizes are just 2 or 3 or 5 microns across. So therefore, one has to do everything on the microscopic scale, and the signal to noise ratio is bad. So we have to apply our methods to improve this signal to noise ratio and to get the signal out and to study physics. Okay. Now, let's come to magnetic fields now. I would like to come to magnetic fields. When we have to create strong magnetic fields in the lab, there are various methods. The most well-known method is using electromagnets. We know all of that because in our childhood we have taken a piece of nail, of iron nail, and we have rolled a wire, insulated copper wire, many turns on this iron nail. We put a battery across this wire, and then we see that then the iron nail becomes magnet. It starts to pull keys and paper clips and so on. But a bigger version of that is needed, of course, in the laboratory, because we need large electric fields, and we create electromagnets like this. Now, an electromagnet like this weighs like 400 kilos. There are two coils here, these two coils, and these coils need a current of like 200 amperes. In our homes, at one point, normally we do not use more than 10 or 15 amperes. Okay, 15 amperes, maybe 20 amperes. That's the maximum we use when a geyser is also on and induction heater is also on. But in this magnet, we need 200 amperes, lots of power. And then we need, for example, 6 to 8 kilowatt of power supply just for this magnet. And once we charge this magnet by 6 or 8 kilowatt of power supply, it becomes very hot because it's copper. It will dissipate heat. And all this power has to be, all this heating has to be drained out. And what we do is we use water lines. There are no, water lines are not shown, but we use water lines. We use water lines to pass water through these coils and then chill the magnet using this, essentially these water lines. So cold water goes in and hot water comes out, and about 5 to 10 liters of water is needed per minute to pass through to keep the magnet cold. And this way we can create magnetic fields of the order of 3 Tesla in the laboratory. 3 Tesla is a large number. We know that our ferrite magnets, the black ones which we happily put on refrigerators, are just 0.01 Tesla or 100 Gauss, something like that. So this is 3 orders of magnitude larger than that. Okay. If we have to go for larger magnetic fields, then we use superconducting magnets, essentially a superconducting coil similar to this coil. Now there is a superconducting coil. It's dipped into liquid helium. It becomes a superconductor because now it's cold. It does not dissipate any energy because it's a superconductor, zero resistance. Then probably a few hundreds of watts of power supply and a current of 100 amperes can be, or 200 amperes maximum, can be used to create magnetic fields these days of the order of 21 Tesla. Okay, so this is how superconducting magnets work, and then they can take us to a large, very large field. The only problem is that they use liquid helium, and liquid helium is also very expensive. This is an expensive resource. But if we need even larger magnetic fields, what we do is we use these electromagnets which are available, or these magnets, simple looking like magnets but very large, which are available only at some very special facilities in the world. For example, this is available in France or in Grenoble. This is a picture from Grenoble. You can see I have put Einstein for scale here. So this is a very large magnet. There are these large tubes which need lots of water for cooling as well. I will tell you about that. Similarly, there are very few places. One is in Tallahassee in Florida, there where such magnets are available, or in Nijmegen in Netherlands there are these magnets, or in China or in Japan these magnets are available. But there are only 5 or 6 places in the world where such magnets are available, and one can create magnetic fields like 35 Tesla using these. Now these are resistive magnets. They need very large power to run, like few tens of megawatts power is needed. Essentially, one can think about it in the following way, that a Rajdhani train is pulling at with 6 megawatt, and you need 4 or 5 Rajdhani trains together, equivalent power of that, to create to charge such a magnet. Now they need very large current like 50,000 amperes, and because this large current is passing through the coils, then you need very giant water coolers which need like 300 liters of water to pass through every second. If you don't trust me, I have a better picture of my colleagues working in Grenoble. You can see these water chiller lines where 300 liters of water is passed through in this magnet, and the water enters at like 16 degrees centigrade and leaves at 95 degrees centigrade. It's actually boiling hot when it leaves. So such large facilities are available only at few places in the world, and one can create fields of the order of 35 Tesla using this. If we combine these resistive magnets with superconducting magnet, we can go to the fields up to 45 Tesla these days, which is in Tallahassee. Grenoble is also trying to make one such large magnet, where the core is a superconducting magnet. I have to check. And one of them, so there are these coils where one is the superconducting and surrounded by another electromagnet and so on. I have to check if the core is superconducting. Yes, I think the core is superconducting. Okay. Now, if one has to produce, okay, so here the magnetic fields are actually continuous fields, meaning one has to pass current continuously through the magnet, and the magnet is continuously producing this large magnetic field. But if we have to go for even larger magnetic fields, larger than 45 Tesla, then one cannot produce continuous fields. One has to create pulsed magnetic field, essentially very strong pulse of a magnetic field which survives maybe for 10 milliseconds, and then the field decays. So for 10 milliseconds, you have the time to perform your experiment. And such experiments are performed by using a condenser bank. So you have a condenser bank, a very large capacitor bank. And this large capacitor bank discharges lots of energy, few megajoules from a coil, inside a coil. And this coil charges up and produces a spike of magnetic field, and then the spikes goes down. So one can create fields like 100 Tesla without blowing up the coil. Essentially, the coil wants to blow up. There is something called Maxwell stress. This Maxwell stress, meaning this is essentially a Lorentz force of the electrons on the coils, and this Lorentz force is an outside force and tries to break the coil. So without breaking, one can reach 100 Tesla of magnetic field. But if we have to produce even larger magnetic fields, again, these are pulsed fields, but what one can do is we can allow this coil to break, and this coil then blows up, lots of energy is passed through, and a field of the order of 1000 Tesla can be produced. I have certain videos. I can show you one, but the sound will not be transmitted to you, unfortunately, but I will just play this video. This is a video from Japan. So you should focus here in this region. Okay, so this was an explosion. This explosion essentially meant that lots of energy was passed through a coil, and the scientists have come here to see that their experiment has successfully been done. So essentially this coil has blown up, but before it blew up, there was a spike which was produced of 210 Tesla for a few microseconds, and one has to do this experiment within the few microseconds. Of course, this is an explosion, so coil blows up outside, so sometimes sample survives, but many times the sample also blows up. Okay, now let's combine magnetic fields and light, and the area is called magneto-optics. This area started with Michael Faraday. And this area is a very important area of science, of experimental science, because using magnetic fields and light, one can learn a lot about magnetic moments in the material of the electrons and holes and so on. The idea is the following. Michael Faraday showed that if there is a linearly polarized light, which is passing through a material, and there is a magnetic field which is applied along the direction of propagation of light, then the light which is coming out of the material, its plane of polarization rotates. So I am coming with this, the plane of polarization rotates. Now, this rotation of plane of polarization is also called Faraday rotation, and the effect is called Faraday effect, which I told was discovered in 1840s. Now, why this effect happens is due to the following reasons. A linearly polarized light can be written as a right and left circular polarized light. Now, right and left circular polarization have different magnetic moments, +1 and -1. We know this. And the material under magnetic field, when the light is passing through, the different magnetic moments, the right and left circular magnetic moments, they interact different with the material in the presence of magnetic field. Meaning the material offers different refractive index to the right and left circular polarization. And due to this different refractive index, there is a phase difference between right and left circular components. And this phase difference, once the superposition state of this right and left component again comes out from the material of the light, then the phase difference leads to a rotation. One can calculate it easily that this phase difference leads to a rotation of the plane of polarization. So this effect is called Faraday effect. Now, this effect is very important because as the material's magnetic moments interact with the light, because the material's magnetic moments, for example, it's a ferromagnetic material, then its magnetic moments might all be aligned parallel to one another in certain direction. And then I apply magnetic field, I can either reverse them and so on. But suppose they are all aligned in the certain direction, then circularly polarized component, one of the circularly polarized component will interact differently with these spins of the material, because the spin has a certain magnetic moment. This adds up with the magnetic moment of light or subtracts from the other components. So the two components of right and left circular polarization interact differently with this spin polarized state in the material. Spin polarized meaning one of the spins have larger population compared to the other spins. So therefore we can study about the spin polarized states, or we can study about the magnetic moments which are present in the material just by looking at this Faraday rotation. Similarly, many times it's not possible to pass the light through the material because the material is opaque. Therefore, what we do is we just reflect the light from the material, reflect polarized light from the material. And this reflection of light also appears as a rotated light. Essentially, if we shine this plane polarized light, and then the polarization of light rotates by angle phi k. So this is the Kerr rotation. Essentially, in the Faraday rotation, it's a transmission which leads to a rotation of plane of polarization. In Kerr rotation, it's reflection which leads to rotation of plane of polarization, and both of these effects give similar amount of information about the properties of the material or the magnetic properties of the material. These effects are nice because they are not destructive, they are non-destructive. One do not have we do not have to destruct the material, apply contacts and things like that. All we have to do is reflect light or transmit light and measure Faraday and Kerr rotation, learn about the quantum states in the material related to the magnetism. Okay, this is a typical magneto-optical setup. So essentially what is happening is the following. There is a cryostat in which the material is lying down here somewhere inside the cryostat, and this material is cooled to 4 Kelvin. That's why this is kept in this cryostat and it's in the vacuum. There are two windows around the material. The material lies inside a copper cold finger of the cryostat, which is surrounded by this aluminum shroud, and then there are two windows. And light has to be passed through the material for seeing the Faraday effect. So what's happening is there is some light beam which is coming, and the light then passes through a hole in the magnet's pole piece. So there is a hole in the pole piece that is not shown, and then the light passes through the it focused on the material, and then it passes through, and then there is a mirror which takes the light to the detection stage, and we measure the rotation of the plane of polarization called Faraday rotation. Okay, so with this, I come to an end of all the fundamental concepts. And in the next 25 minutes, I will start giving you some examples from the latest research, which we are doing and which are happening around the world in this area of research. And as soon as the time gets over, or maybe the last 10 minutes, we can keep for questions, and I will stop at 3:50. So I think we have 25 minutes for that. Okay, so let me come to the first part of the talk, the first part of the results, some latest results. I have many, but I will only show those which are permitted by time. We will not rush through, otherwise there is no sense of the lecture when people are not able to understand. We will make it slowly. So, there is some law in physics or in solids or in even chemistry called the Beer's law or Beer-Lambert's law. This law states that if I have a medium which is an absorptive medium, meaning if I pass light through this medium and the light is absorbed by the medium, then the law says that as I am increasing the thickness of the medium and I am passing the light, more and more light gets absorbed. In fact, the law says that the intensity of the light that's coming out of the material decays exponentially as the thickness is increased. Okay, the question is, does this law hold for the solids? This is a question that we asked like 3 years ago when I joined here as a assistant professor of physics. Now the thing is the following. I mean, people start to ask like, why do I question this fundamental law? I had some reasons to question this, and then I set out with my students to check if this law actually holds for solids at all or not. Okay, let me tell first what the law is. Okay, this is the student who actually worked on this. She is Bhumika, and she is now a fourth year MSc PhD student. She has worked on this project. Now, the point is the following. This law says that as the thickness increases, if I ignore all kinds of interference effects in the material, which is what Beer's law follows, there are no interference effects in the Beer's law, then then the absorption should keep rising and then it should saturate as the thickness is increasing. This is what the law said. The absorption, the intensity of light that's coming out of the material decays exponentially with an absorption coefficient called alpha. So I naught is the incident intensity, IX is the intensity that is coming out. The question is, is this law followed for solids? In fact, this law has never been checked for solids at the nanometer thickness scale. This is very interesting. This was very interesting to us when we were doing this. And what we did was we first checked theoretically if these curves, which are the Beer's law curves of Beer's law, they should hold for the solids. And what we do is, suppose I have a layered material, I put it on a substrate. So this is the crystal, this is a space axis. So there is air, there is a substrate, and on the top of the substrate there is a crystal, and then there is again air. As simple as that. So we have a substrate, we keep on placing some crystals on the substrate. And then we check theoretically using something called transfer matrix method what this law should look like. And I will not go into the details. Essentially what we are doing here is very simple. We have light of I naught intensity shining on this air crystal interface. Some light is reflected, some is transmitted. This transmitted light propagates and it captures this I0 e raised to minus alpha d here, and then some part is reflected, goes into a substrate, and then the substrate reflects and some part goes through, and so on. And this cycle continues, multiple reflections, lots of reflections. So once you do this, this is called transfer matrix method. We find theoretically that this law should get strongly modified. In fact, there should be these oscillations. There should be these oscillations. And these oscillations should deviate strongly from this law, from the Beer's law. Now, this is all theory. What do we do for checking experiment? Well, in experiment, what we have to measure absorption is a material. Suppose I have certain crystal like tungsten disulfide, which is kept on a substrate. I measure its reflection, I measure its transmission, and then I do 1 minus R minus T, which is absorption. I have the absorption spectrum, meaning on the x-axis I have energy or wavelength, on y-axis I have absorption. I need total absorption, so I integrate it over the whole spectrum. So essentially, integrated absorption is what I need for every thickness. Therefore, I need many thicknesses of the material, because this plot here at the bottom has thickness on the x-axis and integrated absorption on the y-axis. So for each thickness, I need to integrate the absorption spectrum, and I will have one data point for each thickness. So what we do is we deposit lots and lots of these crystals on the substrate. We measure their thickness using atomic force microscopy. We keep on measuring their thickness and keep on measuring their absorption and the integrated absorption. And this is what we have here. The setup which I have discussed with you. So one has to reflect the light, one has to transmit light, and so on. Okay, so this is an example of reflectance, transmission, and absorption spectrum of a monolayer, of a single layer of tungsten disulfide. So there is an absorption spectrum here, which is 1 minus R minus T. Similarly, for a thick layer such as 100 nanometers, I am showing you another absorption spectrum, which is here. In fact, we measured this on many samples. Let me show you. For example, we had two materials, MOSC2 and WS2, and lots of absorption spectra for various thicknesses are measured, and then this curve is plotted. And this curve, the experiment falls directly on the curve which we had predicted in the previous slide by just taking care of interferences. Now, the point is, this has never been tested earlier. The reason is probably that these samples are layered materials, and people have not worked for such problems on layered materials. Before layered materials, there were other materials such as gallium arsenide and quantum wells and so on. And it was very difficult to create different thicknesses of quantum wells and create a full histogram or full statistics to check this law. But now we find that experiment and theory are completely in sync with each other. They are in excellent agreement, and we have submitted this for publication. Essentially, we find that these are only the interference effects, because in the theory we had imagined that there should be interferences here, which means that there will be light which will be reflected and which will be coming back, and there will be phase matching and so on. And all these effects, once we consider into picture, we find that the Beer's law gets strongly modified. This is one of the results. Okay, let me move on and check Beer's law for all other kinds of solids. At the moment, I only showed van der Waals semiconductors. So when we calculate, now I do not do experiments on all other kinds of materials. Only calculations are enough, because we have shown using two materials that the calculation and experiment are agreeing with each other. We find that all kinds of materials, maybe those are magnets like two-dimensional magnets, or conventional semiconductors, silicon, gallium arsenide, or semi-metallic like aluminium or silver or graphene or metallic, meaning gold. So all these materials, they have strong deviations from the Beer's law, which must be considered by the textbooks. Essentially, why these are important is the following. Suppose that I have a material such as this MOSC2, suppose this brown curve which I am imagining, and I want to create a photovoltaic using this material. Now, if I use a thickness, if I want to create ultra thin photovoltaic, if I use a thickness of this photovoltaic at 40 nanometer or 10 nanometer, I see the same absorption. Therefore, why should I use 40 nanometer when I get same absorption using 10 nanometer? Therefore, one can optimize all the absorption based devices using this knowledge. Similarly, in fact, the absorption actually goes down here. For example, in going from 60 nanometers to 80 nanometers, absorption is going down. So counterintuitively, I should not use 80, I should use 60. And this knowledge will be very useful for the future. This is what I meant. Okay, I will not go further into details. Some next results which I wanted to show are using magneto-optical spectroscopy, because I wanted to show some results on magneto-optical spectroscopy. Now, suppose I have placed this two-dimensional hydrogen atom which I have been discussing in the magnetic fields. The question is, what happens with this hydrogen atom in the magnetic field? The answer is that the energy of this exciton or this artificial hydrogen atom, it gets modified. What's happening is there is this ground state energy Eg in the absence of magnetic field, but then there is Zeeman turn. This is the Zeeman splitting. Essentially, there are these holes, there are these electrons, and the energy levels are split for holes and for electrons. So therefore, initially, if a transition was doubly degenerate, for example, this heavy hole to electron transition was doubly degenerate, now this degeneracy will be lifted. So we should be able to see Zeeman splitting. Not only that, I had told you that the electrons, single electrons in magnetic fields, behave quantized. Their energy is quantized due to magnetic field. So this is also called magnetic confinement. You apply a magnetic field perpendicular to an electron gas. The electron wants to stay at its own place because it starts to cyclotron orbit, and then its energies are quantized. Not all cyclotron orbits are allowed, only some of them are allowed. Now, all these effects can be studied in terms of excitons. For example, let's study Zeeman splitting. This was a spectrum which I showed you for this quantum well, where there are heavy hole to electron and light hole to electron uh, transitions, and these resonances are ground state exciton transitions. So in the absence of magnetic field at 4.2 Kelvin, there are these two transitions which we are seeing. And both of these transitions are doubly degenerate, meaning if I use right or left circular polarization, I will get same answer. That is what is seen. Now, when I apply magnetic field, there is Zeeman splitting, and the Zeeman splitting is G mu B B, meaning the plus state will go down because this is electron, minus will go up, and there is a negative G factor for this. Similarly, for holes, there will be a Zeeman splitting here. So right and left circular polarizations in the end will have different energies. Meaning, the excitons which had the same doubly degenerate line for heavy hole and for light hole I am not showing here as a transition. This was doubly degenerate, but now the degeneracy should lift if I use right and left circularly polarized absorption spectrum. That's the key. I have to use right and left circularly polarized absorption. I have to measure right and left circular polarized absorption. So this is what we do. We apply a magnetic field of 8 Tesla, and we notice that there are these right and left circularly polarized absorption. One is blue, one is orange. This blue and orange is split here in intensity. In the light hole, this is like heavy hole. For light hole, the splitting is much more easily visible. But you notice that we needed a very large magnetic field, like 8 Tesla, for seeing this splitting nicely. Zeeman splitting is small. For heavy hole, it's even smaller. Very large field is needed, and this splitting for heavy hole is very small. The G factor for heavy hole is very small. G factor for light hole is large, apparently. So a large field is needed. That is the point. Okay. What about these excited states of excitons? Okay, so the point is the following. Earlier, I had told you that there are these excited states of excitons which should be here. Now, what this Landau quantization does is, for electrons and holes, it pulls the electrons and holes together because it localizes them. Their wave functions come together. For the excited states, this effect is so drastic that these electrons and holes wave functions, once they are pulled together, they are squeezed together, they blue shift actually, meaning the excited states which I expected to be somewhere there, now they will be blue shifting. Once they blue shift, then we should be able to see these excited state resonances better. So magnetic fields make us to see the excited state resonances better. Also, since the wave functions are squeezed in for electrons and holes, which means that now they are spending more time close to each other, so their absorption strength should also rise. The oscillator strength should also rise. So we should be able to see the Rydberg states or the excited states of excitons or these hydrogen atoms rather easily. And this is what we see. So there are these ground states which are available to see without magnetic field, and here, but with magnetic field, the excited states are visible as well. These are n equal to 2 and n equal to 3, heavy hole and light hole, excited states of excitons visible. Therefore, the magnetic fields enable us to see excited states of excitons. But here only a few excited states are seen in this absorption spectroscopy or circularly polarized absorption spectroscopy. Of course, I am writing here as photocurrent, but photocurrent is a measure of absorption. Here what I am doing is I am creating electron hole pairs or excitons, and I am as many electrons and holes are created there or excitons are created, as much photocurrent I will get. I will pull electron and hole carriers through some electrodes, and that is a measure of absorption. So more photons are absorbed, more current is created. Essentially, it's proportional to absorption is what I mean. Now, here only a few excited states are resolved, n equal to 2 and n equal to 3. The question that can be asked is, what if I want to see many more excited states? What do I do? Because in absorption here, I notice that the signal to noise ratio is bad and a few excited states are absorbed. If I am able to improve the signal to noise ratio of my technique, meaning if I am able to see this signature and weaker signature with a better precision in terms of signal to noise ratio, because here the noise level is this, if I improve this noise level by a factor of 1000, I should be able to see many, many weak signatures as well. And there are methods in experimental physics called modulation spectroscopy method or differential spectroscopy methods, which make us to see these very weak signatures in the spectra. What these methods do is the following. So, whenever there is a resonance in the material, this resonance should appear in the absorption spectrum as a peak. Now suppose I'm able to move this resonance in the left or right direction in energy. Suppose I move this resonance left and right periodically in energy, and then I have a part of the spectrum which I have a part which is not moving, meaning which is not modulated. I will tell you how modulation takes place. I will subtract that part from this modulated part. So once you subtract this DC part from the modulated part, you just get a difference spectrum, meaning all the noise that's common to the whole spectrum is subtracted. Basically, one has to make a subtraction. One has to make a subtraction of the spectrum from its own, which is a modulated spectrum. What is meant by modulation? I mean, I am using this word over and over. Let me try to tell what is meant. Suppose I have a dielectric function of the material, meaning I have an absorption spectrum of the material, which is dependent on the dielectric function of the material. And I perturb this absorption spectrum periodically by shining a laser. I'm shining a laser, I'm repeatedly heating the material. As soon as I heat, I shift the resonances slightly towards right, and the material cools down immediately, and the resonances are back. And then I subtract these two spectra, meaning in the presence of laser and without laser. So then at the frequency of perturbation, if I keep on making this subtraction, then what I notice is I just have a differential spectrum. And this differential spectrum tells me in the end that the noise which is common to both of these spectra will be deleted. This will be just subtracted, and what I am left is just the beautiful features of the spectra. Basically, we have to reduce the noise, and therefore the effect of this subtraction is maximum around the Brillouin zones of the resonances. So there are these sharp derivative like line shapes because we are subtracting. There is no DC background because we have subtracted. And this is the example which I told you, that we have a laser which is periodically pumping the sample, and we are measuring the reflectance or absorption spectrum from the sample periodically. And at the frequency of the of this periodic perturbation, we notice differential like spectrum. Here is an example, and this you will understand the power of this technique very soon. So this is an absorption spectrum of the quantum well which I was showing you. We have known this already. We have to look at the orange curve now. Suppose this quantum well had another level of quantization. which is true for this quantum well actually experimentally. So then there will be two more resonances which should be visible. However, these two resonances in absorption are not distinguished from each other. They are broad for some reason and they are overlapping with each other. So we are only able to see one resonance. There should be two. But this technique which is called photoreflectance, these two resonances are actually separated into two because here we are able to see direct difference spectroscopy, and in the direct difference spectroscopy the signal to noise ratio is so nice, the background is all gone. You see the background has come to zero, the blue axis here is at zero, and one is able to see two signatures here. Similarly, we are able to see even some signatures corresponding to the heavy hole and light hole excited states. So once we have excited states, we are able to see using photoreflectance spectroscopy or modulation spectroscopy easily. So therefore modulation spectroscopy is sensitive towards weak features, and what we do is we do polarization modulation spectroscopy, also called magneto-optical Kerr effect spectroscopy. What I mean is, as I told you, in magnetic field, right and left circular polarizations have different response. So what if I directly take the difference spectrum between these two response? And then there are these methods which I will not go into the details. If I am able to measure this direct difference called Kerr ellipticity, then we notice compared to this spectrum where only two excited states are visible, here I can see 15 excited states. Now this is in 7 Tesla magnetic field, this was 8 Tesla magnetic field. You notice that in absorption, the signal to noise ratio is not great. But in Kerr spectrum, the signal to noise ratio is very nice. Directly differences are seen which enable us to see many excited states or Rydberg states of the spectrum of this quantum well. Therefore, many excited states are seen. That's the power of, or that's the beauty of this differential spectroscopy techniques such as magneto-optical Kerr effect spectroscopy. Therefore, using such methods, we are able to see very weak signatures and we can enhance the excited states. Uh, okay, I do not want to go into the details of this. I think I should stop here because then there will be no time for questions. And probably this is the right time to stop because we have covered so much within these 2 hours. Thank you very much, and I am happy to take questions. I mean, I had many more experiments to show, but it does not make sense because then we will be rushing and we are not able to enjoy the science behind those experiments. So it's better to discuss. 2D discussed, 3D also there. Sure. So three-dimensional science has been done since very long time, since many decades, and there is lots of science there which has been discovered using all these methods, magneto-optical spectroscopy or optical spectroscopy. And but since the modern world demands two dimensions because we want to miniaturize everything, we want to reduce the dimensions of everything. Therefore, two-dimensional physics is much more interesting to us. Three-dimensional physics is done since very long. Therefore, I discussed more about two-dimensional physics. Okay, so there is a question from Mr. Jha who says exciton state when n to infinity, then does it lead to Beer's law? Okay, Beer's law does not really depend on excitons. I mean, for Beer's law, what we need is just some material, just some medium which is absorbing. And this absorption can be due to all kinds of processes. You don't even need exciton. You can have free carrier absorption. You can have all kinds of processes. You can even use phonons to absorb light. So Beer's law will still hold. What we find is that when you go to nanometer scale thicknesses, there are very strong deviations from this Beer's law, which also hold. I mean, there are excitons or no excitons. You can go to metals which have plasmons. You can go to all kinds of different materials, and this oscillation, this oscillatory behavior also holds. So that's what we find. So therefore, we have submitted a paper called Universal Deviations from this law in all kinds of materials. Okay. Other question is differential spectroscopy for microwave radiation as well. Well, I'm not an expert of microwave radiation, but all I guarantee is that there are groups in the world which measure, for example, response of some material to the right to the vertical and horizontal polarization, and then they measure the difference of the response. So that will be differential spectroscopy. Similarly, there are antennas which are used for detecting circularly polarized light, for example. So then to check the very small, suppose response of these antenna, when there is a difference between right and left circular polarization, one can do differential spectroscopy there also. So that works as well. So I think differential spectroscopy is also universal to all kinds of wavelengths. Okay, what is the maximum magnetic field that we generate in labs in India, and which lab does it? Devanshuji is asking. Well, maximum continuous magnetic fields that are created in labs in India are of the order of 18 to 20 Tesla. And these 18 to 20 Tesla are created using superconducting magnets in many different laboratories, such as there is a laboratory in Tata Institute of Fundamental Research. There are laboratories, even in IISER Pune, we have up to 14 Tesla in various labs around India, such as in various DST labs also, such as SN Bose Institute, SINP. I know researchers who work with large magnetic fields, up to 16 Tesla easily. But if one thinks of pulsed magnetic field, the pulsed magnetic field can be even larger, and there is one laboratory in India, to the best of my knowledge, which creates pulsed magnetic field up to 35 Tesla, and that laboratory is in IISER, Kolkata. So there is a group called Professor Bhavtosh Bansal's group, where they have created pulse magnetic field facility where they are creating up to 35 Tesla. So that's very nice. So they create pulses of 20 millisecond, and then they do experiments in 35 Tesla. It's very nice. We also have plans to create such pulsed magnets maybe in near future. What is the current state of these concept applications? Okay, so if we talk of applications, the field of two-dimensional materials at the moment is quite premature because it started in 2005, and then that was only graphene. Then it went on to two-dimensional semiconductors in 2010. That it went on to two-dimensional magnetic materials in 2017, and lots of research is being done only in laboratories at this point. However, there are many things which are already out in the market. For example, there are something called single photon emission sources, and there are companies which have created chips of these single photon emission sources, which are very useful for quantum communications. You need one photon at a time for quantum communications, and in these two-dimensional materials, there are certain materials which emit single photons on demand, and that has been created by certain companies. So that is, for example, one application that has been done using these. Others are still at the laboratory level because we are still waiting for large quality and large size wafers of these materials. Many groups are already after this. Lots of companies are after this, and so soon there will be many devices which have flexible electronics. Like imagine if you want a television with you, and this is just a piece of paper, so you fold it and put in your pocket and take with you. That is the world people are imagining in the next 10 years or something. So two-dimensional materials will be everywhere. Already there are these displays such as graphene displays and so on, which are flexible and so on. All flexible electronics is already there, lots of it. Can differential spectroscopy be used for finding the number of layers in a sample? Definitely. I mean, differential spectroscopy essentially means that you need a difference spectrum between the substrate and between, say, the sample. Now, this contrast spectrum is what is essentially used by people for measuring the thicknesses, because there is this visual contrast or optical contrast, which is also sort of a difference spectrum. So one has this differential spectroscopy, which is very sensitive to the number of layers. In fact, if we notice, we measure the spectra, as a function of layer thickness, we find that this different spectra, for example, for a monolayer, if it looks like this, for bilayer, it's like double. For trilayer, it's like a bit more. For layers, it's a bit more. So therefore, there are large differences between different layer thicknesses in all these spectra. So that is useful. Definitely. Thank you all for your questions. I'm happy. I'm happy to take further questions. I'm here for a few more minutes, surely. Dr. Kumar, you are muted.
Yeah, sorry. Thank you so much. It was really very nice talk. And interestingly, you covered uh, more or less from basic to the advanced altogether, everything related to this topic. And this was also good to see some advanced results. I hope you enjoyed the queries and questions.
Definitely.
And yeah, so uh, regarding this quantum material and this topic, quantum technologies, certainly these optical probes are really important. It is very difficult to seize these features using electronic probes.
Yes.
So that way we have included this these
Yes.
techniques with this course. And I remember it was hectic for you to accommodate the talk, but still you could manage. So thank you once again. Thank you very
Thank you
much.
very much. Thank you very much for your
Yes.
flexibility as well. I just want
Yeah.
to add one thing, since you said the importance of these probes. Most of the material or most of the characterization technologies at this point we have to import in India, unfortunately. In fact, 95% of the equipment is imported in India. So for the participants, I just want to tell that our laboratory at IISER Pune also has created a company recently where we are working with the government of India, and we are building our own techniques and technologies within India so that the import dependence is reduced. I mean, this company is called Yantram Instruments Private Limited. We have just established this company, and we are already quite ahead in making lots of prototypes, and you will hear from us at some point once things are commercialized.
Okay. So it is really nice to know. Yeah, this is true. Uh, in India, we have uh, several dependencies when it comes to the advanced technologies.
Yeah,
So it is better that we get our own companies and our own production.
exactly.
Yeah. So uh, as a requirement, or you can say a request from the participants, we will be needing the slides.
Okay,
Many participants are also uh, asking for the slides,
sure.
and
I will
yeah,
share it with you.
yeah, and then Kavita RB, she want to listen the company name again, so that
Okay,
maybe she's interested.
let me write the name here. But this company has just been registered, and the operations have to start probably in 6 months.
Okay.
Yes, the prototypes are ready. Maybe we are able to launch first of our prototypes, which are essentially magnets. The point is, I mean, these magnets which we buy from abroad or from India, they are super expensive and they're very heavy. Think about it. In my laboratory, there is a magnet which produces 1.8 Tesla magnetic field. It weighs 2000 kilos. We have done lots and lots of R&D in the last 8 months with our people here, and we have brought down the weight to 200 kilos. So essentially by a factor of 10, then the power has come down by a factor of 6 and so on. So this is the first product that is going to come to the market, and there will be many more.
Okay, sir.
Thank you very
So
much.
with this, thank you so much, sir.
Thank you very much. Have a nice
Thank
day.
you. Yeah, same to you. So for the participants, we'll have another talk by Dr. Abhiram. Maybe we can take a pause for 2 minutes and then we move to the next topic. Dr. Abhiram is already online, so we'll be starting the next talk shortly. Good afternoon, Abhiram sir. How are you?
Hello, sir. Yeah, I'm good. How are you, sir?
Yeah, perfectly fine, sir. It was nice to see you.
Hello, can you hear me?
Yes, I can hear. It is nice to see you. So, we just completed the previous
Yes.
talk and we'll begin in 1 minute. So, should be fine, I think, right? So, I will
Okay.
just introduce
Yes.
a brief introduction and then formally we can start the talk.
Okay. Yeah.
Okay, so good afternoon, all, once again, and welcome to the next session by Dr. Abhiram Suri. Dr. Abhiram Suri, he's from Department of Physics, University of Hyderabad. He was a DST inspired faculty at ISER Bhopal earlier, and also postdoctoral fellowship at Department of Physics, Indian Institute of Science, Bangalore, and postdoctoral fellow at International Center for Theoretical Sciences, Bangalore, just after the PhD. His research interest involves the theoretical description of quantum transport phenomena in various mesoscopic systems, including topological insulators, Majorana fermions, non-Hermitian systems, antiferromagnets, graphene, spin orbit coupled systems, and I think there is a long list. So, in he's basically theoretical physicist working in the quantum materials area. Today, he will be covering a little bit of introduction to the topological phases of matter, and specifically, he will be giving us the lecture on altermagnets. So, with this, without taking much time, I welcome our speaker, Dr. Abhiram Suri. Thank you, sir, for accepting our invitation, and I invite you to start the lecture. Thank you so much.
Okay. Thank you,
Over
sir.
to you, sir.
Uh, yes, sir. Thank you. Hope everyone can hear me clearly. I
Yeah, sir,
am logged in.
we are not able to see your slides or your screen.
I'll share. I'll share. So I'm logged
Okay,
in
sir.
from
Okay.
two devices. One for this audio, video, this thing, and another for sharing my slides. I'll share my slides. So I hope you can see my screen.
Yes, now we can see the screen.
Okay. Yes. So I'll be giving two talks today. So the first one will be on introduction to topological phases of matter. Actually, I am showing my slides, but I cannot see the slide from the other one. Let me go to this again.
So possibly, maybe, sir, you share the entire screen. So that way it should be possible.
Yeah, entire screen. Yes, yes. Yeah, I'll say stop. Yeah, I'll say stop sharing. So now I hope it has stopped. Yes, I'll share again. Share. Optimize text. Share. Okay. Optimize for video. Okay. Share screen. No, I think it didn't ask anywhere like share entire screen kind of thing. Let me see again. Do you see my slides? No. Share. Okay. Or should I share just the file? PDF file? No, that's also not a good idea. Can you see my screen?
No, sir.
Hello.
No, sir. No. Your screen is not visible to
Okay,
us.
one thing I'll do. Okay. So, okay, now I think something is coming up.
Yeah, now we can see your screen.
Okay, great. Okay.
Yes, this is perfect. The presentation was there. So,
Yes, yes, yes.
yeah.
Okay. Okay, so the first talk that I'll be giving is basically on introduction to topological phases of matter. So, to begin with, this electrons in crystals and energy bands. So that's what I'll tell in the beginning. So in solids, you have atoms that are arranged periodically to form a crystal lattice, right? So the electrons in such periodic crystal, they experience both the attractive force, the nuclei, and repulsion from other electrons. And due to the wave nature of electrons, the allowed energies, they form continuous range of energies called energy bands, separated by band gaps. So one interesting thing is that in individual atoms, the energy levels are discrete. There are only certain specified energy levels. But in solid, when many atoms are put together, they form something called bands. Okay, a continuous range of energies where there are allowed energy levels. Then next, this concept of energy bands, whatever I told you, so this can be used to explain the properties of conductors, semiconductors, and insulators. We'll see how it is. And this is one of the this quantum mechanical understanding of this electrons in solids. So this is one of the very important milestones in the condensed matter physics. Okay, so you see here on the left we have metals, which is so I have taken the example of copper. So here electrons flow easily, um, and basically when you apply a small potential difference, you get a current. So that is what metals are. In insulators, the electrons are tightly bound to individual atoms, and electrons cannot flow when you apply a potential difference. So that is what it is. So let's see what is the important reason why. I mean, to understand this from the band theory point. Okay. So when I say these electrons form bands, so if you see the density of states, I'm trying to draw. I have used this earlier, but I'm not able to. Okay, so let me go back to the slides. Yeah, so basically there are certain energy, there's a range of energy levels which is allowed. That is, so if your Fermi energy lies there, that is when it becomes a metal. So now what is Fermi energy? So Fermi energy in physics, it's basically the energy up to which all the electrons are filled and above which all the electrons are empty at zero temperature. Okay, so this basically applies to these particles called fermions in physics. So in physics, generally, there are two kind of particles: fermions and bosons. And fermions are the particles which obey Pauli exclusion principle, and electrons are one of them. So what is Pauli exclusion principle? For a given quantum state with given set of quantum numbers, that can be occupied with only one fermion or no fermion. So two or more fermions cannot occupy that particular state. That is what Pauli exclusion principle says. And these electrons obey this Pauli exclusion principle, and these are fermions, and they are the ones that are responsible for conduction in metals and insulators. Okay, or in insulators, okay, the electrons are there, but there is no conduction. Okay, so fine. Let us next move on to this effect called quantum Hall effect. Okay, so this quantum Hall effect is a very important effect. So you can see that two Nobel Prizes uh, have been given to this area of quantum Hall effect. One in 1985 to von Klitzing for discovering integer quantum Hall effect experimentally, and the second one is for the fractional quantum Hall effect to Laughlin, Stormer, and Sui. So what is this quantum Hall effect essentially? So you see in the figure on the left that I have, you have a two-dimensional electron gas. So the patch here, that's a two-dimensional electron gas. And along x direction, you apply a current bias. You connect a current meter, I mean current source, and you drive a current. And in the perpendicular direction, the y direction, you measure the voltage. Okay. And not only you do this for a two-dimensional electron gas, you apply perpendicular magnetic fields. So what happens when you apply a perpendicular magnetic field? These electrons, they experience what is called Lorentz force. Okay, what is this Lorentz force? It is QE cross B or QV cross B. Okay, so that is the classical form of the Lorentz force, but the same thing you can write it, introduce it in Schrodinger wave equation. And when you introduce it in the Schrodinger wave equation, you see that the energy levels, they become quantized and they forms what is called Landau levels. So you see in the figure here that there are something called Landau levels. So the blue curves here. So nu equal to 1, 2, 3, 4. This is the Landau level index. So these are the dispersions in the bulk. And on the edge, they turn, near the edge, they turn above. And there are these edge states which carry current. That is what is responsible for quantum Hall effect. So to get a pictorial view, when you apply a magnetic field, these electrons, they move in circular orbits, like you see in the above. Okay, so these circular orbits, but the circle cannot make a complete circle near the edges. That is, on the top edge, you see the blue path trajectory where the circle is not completed. So it's like half circle kind of thing. So there's a path. So that is the path for the edge states. So within the bulk gap, when there's a gap, it means that there are no electrons sitting there in the bulk. But on the edges, there are electrons. So within the bulk gap, there is a edge state. So that is what are responsible for quantum Hall. And these are the Landau levels. And okay, so that is what quantum Hall effect is about. Then I move on to topological insulators. Okay, so there is, I had some, I wanted to show something by writing here in the, oh, it says it's read only. Refresh now. Okay. Coming again. Just a second. I wanted to use this board kind of feature here so that I can explain things with proper equations. So give me a second. I'll log in. Yes, I hope I can use this to draw now. Yes.
Abhiram sir,
Yes.
you may stop sharing your video actually.
Okay.
You
Yes.
turn off your video because of the internet speed. I think some people are facing problem. It is not loading clearly.
Okay.
It should be okay now.
Yeah.
The screen is fine. The screen
Yeah.
is fine.
Yeah.
Yeah.
Okay, so this quantum Hall effect I talked about. So the next is topological insulators. So topological insulators, these are basically, what are these materials? These are basically materials that are insulators in the bulk, but on the surface they are conducting. Okay, so this area of this topology is physics. So that won Nobel Prize in 2016. So this three people, Thouless, Haldane, and Kostelis, these people won Nobel Prize in 2016 for this pioneering this area of physics. Okay, so I had some slides on topology. Let me see. Okay, no, it's not there. Okay, I'll tell with this. Okay, so I told you about quantum Hall effect. This is actually in 1980s. This quantum Hall effect was discovered, uh, or it was experimentally realized, to be more precise. So there is one very nice book for quantum Hall effect. There's a Springer book. Springer is the publisher, and the author's name is Yoshioka. If you want to learn about quantum Hall effect, that's a nice. Okay, so in quantum Hall effect, you're actually applying a magnetic field to two-dimensional electron gas, and as a result of applying a magnetic field, you get quantized energy levels and you get quantized conductance. That is even more important. Quantized conductance means, see, you can actually measure the conductance. That is, you apply a current along x direction, measure. So there is current Ix along x direction. You measure voltage Vy along y direction, and the ratio dVy by dix. This is called sigma yx. This is the Hall conductance. And what you find is that this Hall conductance, this is quantized, this is E square by h into some n, where n is an integer. And this this quantization, it is so precise that this is used in metrology. That's the reason why this von Klitzing, the discoverer of this quantum Hall effect, experimental discoverer, so he got Nobel Prize. So where? Okay, yes, he got Nobel Prize for that. Okay, so basically this, so it's a two-dimensional electron gas where you are applying a magnetic field, and these experiments have to be done at a very low temperature. Okay, that's also another important point. And so the next question is, so can you get this kind of Hall response even when there is no net magnetic field? And the answer is yes. And this answer was given in around 1988 by Haldane. Okay, so that is called Haldane model. I'll explain you what is Haldane model in a brief while. So before that, let me tell you continuum and lattice models for metals. Okay, so what is continuum model? Continuum model is, you can write down the Hamiltonian H equal to T square by 2m. Now, what is P here? This is a free electron free Hamiltonian, right? So what is P here? P is an operator. So I can write this as minus h cut square del square, or instead of writing it as del square, I can write it as grad square. So this is in 2 or 3 dimensions divided by 2m. This is the Hamiltonian for free electron Hamiltonian. So the solutions of this, it's e to the power of I kxx plus ky y. These are the kind of solutions that this admits. Okay. Now, you know that in crystals, it is not a continuum material actually. It's a lattice. So how do you write down a lattice model that is equivalent and which kind of captures this effect? So for this Hamiltonian, for the same kind of Hamiltonian, you can actually write in the second quantized language, you can write something like h equal to, so I'll write it in one dimension, it's equal to summation over n minus t. So t is the hopping amplitude, c dagger n plus 1 cn plus c dagger n cn plus 1, where cn and c dagger n, cn is an annihilation operator, c dagger n is creation operator. So what does this do? It's a mathematical thing. So it basically creates an electron at site n. So n equal to 1, 2, 3, 4. This is a lattice actually here. Okay, 1, 2, 3, 4, 0, minus 1, minus 2. Okay, so electrons are basically not confined here. So they are basically hopping. That is what this describes. Okay, so the dispersion relation from this you can obtain. It is basically E equal to minus 2t cos k. Okay, so what is k? K is the wave number. Okay, and h cut k, that is like the momentum. So this dispersion in the lattice, this is equivalent to this p square by 2m dispersion in the continuum near the band bottom. How can you see that? Near the band bottom, cos k you can explain, you can expand it as 1 minus k square divided by 2. So this E you can write it as minus 2t into 1 minus k square divided by 2. So which is actually minus 2t plus t into k square. So this t into k square, whatever you have, you can associate it with h cut square k square divided by 2m. So what is m here? M is the effective mass. Okay, so this is the connection between lattice model and continuum model. And in a lattice model, you can actually make a square lattice in 2 dimensions if you want. Okay, so you can make a square lattice. You can also make honeycomb lattice. Okay, so for this Haldane model, what Haldane did was he made a honeycomb lattice. So honeycomb lattice means it is like graphene. So I'll draw the lattice. So it's something like this. And it will continue. The same structure, it will continue in all directions. Okay, so this is honeycomb lattice. Now you see in this honeycomb lattice, there are 2 kind of atoms. One is in the shape of Y, that I call A, and the other is in the shape of inverted Y, which I call it as B. So A kind of sublattice and B kind of sublattice. These two kind of sublattices. Okay, fine. Now, so basically, what Haldane did was to get this Hall response. In not only you have this kind of lattice, you have to apply magnetic field on top of this to get Hall response usually. But he didn't want to apply a net magnetic field. So what he did was he so this is a purely theoretical kind of model. So you have this next nearest neighbor poppings, right? So there are these kind of this triangles. So in these kind of triangles, he put a flux phi, and there are these two opposite kind of triangles, which is basically I'll draw it with green lines. So here in this green triangles here, so here he put magnetic flux minus phi. Okay, minus phi in the green things, and in the magenta ones, flux phi. So the net flux is 0. But here you get Hall response. That is, you will get a gap in the bulk, and the edge states will be conducting. Okay, so this is the first example of this topological insulator. So this is due to Haldane model. I don't remember the exact year. If I remember correctly, it is 1988. So that is Haldane model. So then after this, so one had to wait for a long time. So that is in around 2009 or so. Let me look at the slides. So around 2009 or so, there was this Z model, Bernegwig, Hughes, and Zhang. Okay, so in that model, they showed, I'll not write down the explicit model, but in this Bernegwig, Hughes, Zhang, so this is called EHZ model. They wrote down a Hamiltonian and showed that it has insulating bulk and conducting surface or conducting edge. Okay, so what does it mean? So first they wrote down a model for topological insulators, which is basically you have a 2D like a sheet. It's a planar sheet kind of thing, where in the bulk there is no conduction and it has an edge, right? So on the edge there is conduction. So electrons can flow on the edge. Okay, so that is what it is. And this was first theoretically predicted and then experimentally realized. They not only wrote down the model, but they also predicted in which material this topological insulator can, this behavior can show up. So it was basically HGCDT heterostructure. Okay, HGTE, CDTE, cadmium telluride, HGC. So the CDT, HGT. So this is where this phenomenon was shown. And then yes, so you can see in the picture. So basically on the left side you have 2D topological insulator. There's a gap, bulk gap, which means that if your Fermi energy is in the gap, it's an insulator. That's the one on the left side. In the middle you have topological insulator. So that is, you have green lines, which is actually dispersion for the edge state electrons. There is forward moving modes, backward moving modes. And not only that, there are forward moving modes and backward moving modes. The forward moving modes are upspins and backward moving modes are downspins. This property is called spin momentum law. Okay, so this is the Hamiltonian actually. H cut VF sigma Z K. K is like the wave vector, or H cut K is like the momentum. We can replace it with momentum operator minus I del by del x. And what is sigma Z? Sigma Z is the Pauli spin matrix. So this is what locks spin to the momentum. Okay, so this is 2D topological insulator. In a 3D topological insulator, you have a 3-dimensional bulk, okay, and 3-dimensional bulk and the 2-dimensional surface. And three-dimensional bulk is an insulator, and two-dimensional surface that you have, that is a metal. And this is the dispersion, the one that you see here. This is the dispersion on the right. Basically, there is spin momentum blocking there also. And the Hamiltonian, you can write it down like this: h cut vf sigma x ky minus sigma x. Actually, there's a typo here. It's sigma x ky minus sigma y kx. Okay, so this is actually massless Dirac equation in 2 dimensions. Okay, so that is three-dimensional topological insulator. So one interesting thing, effect that this three-dimensional topological insulator shows is planar Hall effect. So what is planar Hall effect? So when you apply a magnetic field, as I said, there is this Lorentz force, which is there classically also. But there's also another thing which is called Zeeman effect, that this magnetic field uh, kind of shows. That Zeeman effect is basically you have these electrons which are spin half particles, right? So electrons not only have charge, but they also have spin. So the spin is represented by this sigma, vector sigma. So this magnetic field also couples to the spin, that is B dot sigma. So that is the Zeeman coupling. So because of the Zeeman coupling in the Hamiltonian, okay. So this, so as I said, there is this Dirac cone. So this is called Dirac cone. Whatever picture I'm showing, the blue cone and the red cone that is here. And when you apply a Zeeman field in plane, what happens is that when you apply magnetic field in plane, so this Dirac cone shift, and not only that, so the magnetic field, it shifts in a transverse direction. The Dirac cone shifts in a transverse direction, and due to in-plane magnetic field, there's a transverse voltage that appears. This is called planar Hall effect. So there are experiments also on this planar Hall effect in topological insulation. This thing, this planar Hall effect, it also shows in spin-orbit coupled systems, but in topological insulator, it was interesting to see this planar Hall effect. And this is due to Zeeman coupling and not due to Lorentz force. So fine. Next, I'll go to graphene. So this graphene, this Andre James and Novasolo, these people won Nobel Prize in 2011 for exfoliating graphene from the graphite. Okay, so this was basically experimentally a Scotch-tape method by which they separated this individual sheets of graphene. So what is graphene? Graphene is basically, it's like graphite, but it's a single sheet of carbon atoms, and which is arranged like this, whatever figure I have in the left. So that is the graphene lattice. It's a honeycomb lattice essentially. And the dispersion, electronic dispersion, if you see for graphene, that is shown on the right. So what are the key properties of this? So the three key properties are, it has high mobility. That is, when you send an electron in a metal or any conductor, there's something called mobility, which kind of captures how easy it is for electrons to travel in the medium. And this is quite high for graphene. And the other feature is quantum Hall effect. As I said, quantum Hall effect, you have to go to very low temperatures, but in graphene you can perform quantum Hall effect experiments at room temperatures. That's the specialty of graphene. And not only that, there is something called Klein tunneling that happens in graphene. So what is Klein tunneling? So you all must have come across in the quantum mechanics course that if you have a barrier, classically if you have a barrier and you send an electron or any particle, so let's say you send a particle across a barrier, if the particle's energy is less than the barrier height, it will reflect back, right? That is a classical thing. But quantum mechanically, this particle can tunnel through this barrier, right? It can tunnel through, and there is a probability of transmission, let us say, that is T, and there's a probability of reflection. There's a reflection probability R. And whenever there's a barrier like this, if you take Schrodinger wave equation, there is always a finite reflection probability. Okay, and transmission probability is not 1. That is, everything that you send will not pass through. There is some fraction of particles which will reflect back. So this is the well-known standard quantum mechanics. But if the Equation that is obeyed by the electrons is massless Dirac equation, and you send the particles at normal incidence. That is, so this is the barrier, let us say, in 2 dimensions, let us say. So this is the barrier region, and you send the particle at normal incidence. That is, normal means like 90 degree to this barrier thing. Then there is no reflection. Everything gets transmitted. That is called Klein tunneling. This is a phenomenon in high energy physics. Okay, Klein tunneling. Because this basically originates from relativistic version of the Schrodinger wave equation, which is called this Dirac equation. There, this Klein tunneling is very commonly known. But what happened in graphene was that the dispersion shown by the graphene electrons is same as that for the massless Dirac equation. So for normal incidence, whatever you incident, that tunnels through perfectly. There is no reflection. So that is one interesting phenomena of high energy physics which was realized in condensed matter systems. Okay, so that is about Klein tunneling in graphene. Then I'll talk about Andreev reflection a little bit. So let us go to superconductors. So what are superconductors? Superconductors are materials where conduction of electrons happens without any resistance. What is the reason for this? The reason for electron transmission without any resistance, that is the formation of Cooper pairs. One can write down a Hamiltonian for superconductor. So there you have again e square by 2m kind of term. Then again there is another term which is called superconducting pairing, which opens up a gap in the spectrum, or which opens up a gap in the dispersion. So that figure, it is shown here. This is the energy on the y-axis. On the x you have kx, ky. So there is a superconducting gap that you can see clearly in this. Okay, so there is a superconducting gap, and within the gap a single electron cannot go through. Okay, so now let us consider a junction between a normal metal and superconductor, and you are sending an electron in the normal metal, let us say. So you're sending an electron in the normal metal onto the interface, normal metal superconductor interface. Then because of Cooper pairs in the superconductor and there are no single electron excitations in the superconductor within the gap, Cooper pairs go into the superconductors, and whatever reflects back is a hole. Why hole reflects back? Hole reflects back because to form Cooper pair, it needs 2 electrons, and 1 electron is anyway supplied by you. The other electron is picked up from the below the Fermi sea. Okay, that is below the Fermi energy. There are electrons that are filled. So from there, another electron is picked up, and what appears to you is like hole is reflected back. So this is the phenomenon of Andreev reflection. That is, you send in an electron and a hole reflects back. Okay, so now conductance here, what happens to the conductance in normal metal superconductor junctions? The conductance is basically 2 into e square by h into mod Ra square, where mod Ra square is the reflection, Andreev reflection probability. So interestingly, if this Ra is large, you can get this conductance greater than e square by h. That's an interesting property of transporting normal metal superconductor junctions. Why is that interesting? That is interesting because in Landau-Rüttiger theory, in a normal metal, if you have whatever barrier or anything, the conductance is given by G equal to E square by H into T, where T is the transmission probability. And this T that takes the value, maximum value 1. So E square by H is the maximum conductance possible per electron channel in the normal metal. But in normal metal superconductor junctions, G can be equal to E square by H into 2 into mod Ra square. So this can be more than E square by H. So that's when you think about superconductor, normal metal superconductor junctions. And if there is a bound state in the superconductor, okay, so if there's a bound state, then the Ra, mod Ra turns out to be 1. Okay, that is a signature for a bound state that is there in the superconductor. Okay, so I'll explain this. why this is important. Okay, so before going there, I'll tell you about Majorana fermions, which are topological particles that were discovered in the last 15-20 years or so. Okay, not really 50, yeah, 15-20 years. So basically, there is this thing called Majorana fermions. So these were, what are Majorana fermions? So let me tell you the story behind Majorana fermions. This Majorana fermions, they were discovered by Majorana. So he actually proposed this Majorana fermions in 1931. So Majorana is an Italian physicist. Majorana. So what are these? So these were introduced again in high energy physics. What are the property of these particles? These particles are their own antiparticles. Okay, so in the high energy physics language or quantum field theory language, so let us say C is a creation operator, or C dagger is a creation operator, and C is annihilation operator. So something is its own antiparticle means C dagger is equal to C. Okay, so these kind of particles were proposed by Majorana, and it was predicted that neutrinos are Majorana fermions. Okay, so now coming to the condensed matter world, what is antiparticle? So particle means, okay, you can say electron is a particle, okay, in solids. And what is antiparticle? Antiparticle means it is hole, because what is hole? Hole is absence of electron. Okay, so holes and electrons make particle-antiparticle partners in condensed matter physics. Okay, so this is the property for Majorana fermions, as I said, and this. Okay, so now we have creation operators and annihilation operators, I told you, right? So this is, yeah, so Cn is annihilation operator for an electron at site n, annihilation or destruction operator, and C dagger n, this is creation operator for electron. Okay, now is there any way to make some sort of linear combination of the Cn and Cn dagger so that so let's say psi n is an operator which is actually Cn plus Cn dagger, some alpha Cn plus beta Cn dagger. Now what values of alpha and beta should I choose so that psi n dagger is equal to psi n? That's the question I have. Anyone, any answer? I see some response saying Hermitian, equal, not equal, okay. Phase difference, okay, let me tell you the answer. So alpha and beta are numbers that I can choose, okay. So let us say alpha equal to beta equal to 1. That is one choice actually. That is Cn plus Cn dagger if you take. And now you take dagger of this. This will give you Cn dagger plus Cn. Because double dagger is same as that itself. So Cn plus Cn dagger is Cn dagger plus Cn. So these are same. So this is a Majorana fermion. Okay. So there is another way of making a Majorana fermion, which is basically Cn minus Cn dagger, the whole thing into I. Now when you take dagger, you will get the same thing. Okay. So what this means is that this every Majorana, every electron operator, electron creation or annihilation operator that you have, it is made up of two Majorana fermions. So let us call this as A n and this as B n. So then basically Cn is equal to An plus Bn or An plus Ibn divided by 2. And Cn dagger is An minus Ibn divided by 2. And An and Bn, these have the property that An dagger is equal to An and Bn dagger is equal to Bn. So what is the interesting thing about this? The reason why these are very important is that if you realize these kind of particles, you can use this in developing of quantum computers. Okay, so you can develop quantum computers if you realize these particles. But the problem is an electron has two Majorana fermions, but these two Majorana fermions are always together. The aim now is to isolate these Majorana fermions. So how can you isolate this? So it was given by Kitaev by again a theoretical kind of model. It is called Kitaev model or Kitaev chain, Kitaev model for Majorana fermions. So he came up with a model and wrote it down in 2001. Okay, so I'm not sure if I have enough time to explain this Kitaev model, but essentially what he did was he introduced p-wave superconducting pairing in a one-dimensional chain. Okay, so p-wave superconducting chain in the one-dimensional chain, and then he showed that for certain choice of parameters, for parameters in certain range, you can get two Majorana fermions which are isolated at the ends. So if this is a chain, at one end you will have a Majorana fermion A0, and here you will have Bn, something like this, which is isolated. Okay, and these are in the p-wave superconductors. And then this was in 2001. And then in around 2009, two groups, so one from Maryland and another from Europe and Israel, so they came up with an experimentally realizable model, that is experimentally implementable kind of model, where you can realize this Majorana fermion. So what was that model? What were the ingredients of that new Hamiltonian? So they said you have superconductivity plus spin orbit coupling plus Zeeman field. That is Zeeman field, I told you what it is some time back. So spin orbit coupling is basically, so the spin of the electron is basically L dot S term in the Hamiltonian for hydrogen atom. Okay, that's at the heart of spin orbit coupling. But that appears for electrons moving in certain materials like indium arsenide or indium antimonide. Okay, so if you have spin orbit coupling, superconductivity, and Zeeman field, these three things put together in a quantum wire, that quantum wire exhibits Majorana fermions at the ends. So that was the prediction. This was in around 2009. And in 2000, if I am correct, in 2011 or so, they experimentally observed the evidence for Majorana fermion in this same setup that was proposed by these two groups. And then what was the evidence of Majorana fermion? The Majorana fermion, the evidence is zero bias peak, zero bias conductance peak. So what is zero bias conductance peak? You apply a small voltage bias across normal metal superconductor junction, where the superconductor is replaced by the superconductor plus spin orbit coupling plus Zeeman field. Then at zero energy, near the zero bias, you will see a peak in conductance. So this G conductance versus V. So near zero in the differential conductance, you will see a peak, which should be actually the real theoretical prediction is that this peak should have the value 2e square by h. That is a prediction. But experimentally, they saw a peak and they said that it is due to Majorana fermion. That's an evidence for Majorana fermion. It is experimentally seen peak. It did not, the height was not same as 2e square by h. It was much less than 2e square by h. Okay. Then later there was a lot of controversy because there was one paper which claimed that they saw 2e square by h quantized conductance peak in these systems in a much better experiment. But then it was found that there are a lot of experimental errors in that while doing that experiment, and the paper was retracted back. So there was a lot of controversy around this Majorana fermion. So even now, whether Majorana fermion, the experimental evidence has been seen or not, that's a controversy. The reason for the controversy is that the zero bias peak can appear not only because of Majorana fermion, there are other mechanisms that can give rise to zero bias peak. So the conclusive evidence for observing Majorana fermions is not zero bias peak. So that is the reason for this controversy. Okay, so that is about Majorana fermions. Okay, so and then there is something that I want to tell you about cross-sectional reflection. I'll also kind of cover some of this in my second talk. So what is this cross-sectional reflection phenomenon? So Andreev reflection. So what is Andreev reflection? Let us begin with that. So what is Andreev reflection? So Andreev reflection. So you have normal metal and a superconductor junction. So you send an electron from normal metal and the electron reflects back as a hole. This electron, and this reflects back as a hole. That is Andreev reflection. You incident an electron, reflects back as a whole. That is Andreev reflection. Now, what is cross-Andreev reflection? Cross-Andreev reflection is you connect two normal metals to a superconductor at different places. So there is one normal metal connected to the superconductor here. There is another normal metal I'll connect to the same superconductor at another place. Now I send in an electron from the normal metal. Okay, let me send an electron from the normal metal, and that electron that I send from the normal metal, it can go into the superconductor and come out on the other normal metal as a whole. So there's an electron sent, it will come back on the other normal metal as a whole. This is called cross-Andreev reflection. And why is this important in physics? This is important because when this process happens, a Cooper pair that goes into the superconductor to the ground. The superconductor is a grounded superconductor. Okay, so to the ground of the superconductor, a Cooper pair goes in. So what is this phenomenon? This phenomenon actually is inverse of a phenomenon called Cooper pair splitting. What is Cooper pair splitting? Cooper pair splitting is that you take a superconductor and connect two normal metals, and then apply a bias from superconductor to normal metals. Then what happens? What happens is that when you apply a bias, the two electrons from this Cooper pair, one electron goes in one normal metal, the other electron goes in the other normal metal. And this is called Cooper pair splitting. Okay, so one electron goes in one normal metal, the other electron goes in other normal metal. Why is this interesting? This is interesting because these electrons in the superconductors, in the Cooper pair, they are in the singlet state, that is up down minus down up state. This is the state. This is an entangled state. So this, what you are doing by doing this Cooper pair splitting is you are separating two electrons and their spin is not precisely known. It is the two electrons together, they are in the entangled state, that is up down minus down up state, and these are not in the same place. So these are actually non-locally entangled electrons. So we are actually able to produce what is called non-locally entangled electrons by doing this process called Cooper pair splitting. And whatever cross and reflection thing I told you, that is inverse process of Cooper pair splitting. If you can achieve cross and reflection in a setup, you just reverse the configuration. That is, instead of applying a bias from normal metal to the superconductor, you apply bias from the superconductor to normal metal. Then you will see that the non-locally entangled electrons are produced. Okay, so that is why this cross-on reflection is a very important phenomenon. Okay, in the next talk, I'll discuss some schemes using altermagnets to study this or to enhance this phenomenon of cross-on reflection. Okay, so that is more or less of what I wanted to tell for the first talk. So do we take a couple of minutes break before the second talk, or Manoj sir?
Yes, sir. So, yeah, it was nice. So this is break time, huh?
Yeah, so just a couple of minutes break.
Yeah. So probably you could see some queries already, or we will take those queries after
Break.
the
Okay,
second
sure.
talk also.
Yeah, after the break also we can take questions on whatever I
Fine,
have done
fine,
so
fine.
far. Yes. And then we can
So
proceed with the second part of it.
perfect. Let us take a short break.
Okay. Yes.
Okay, sir. Thank you.
Yeah. Yes. Okay. So can we well, I'm happy to take questions on whatever we discussed till now. Okay, I'm looking at the. So, hello, sir. Can you hear me? I am back from the break. Uh, what about others? Can I? We can have some discussion and continue with the next talk. If
Hello.
yes, hello.
Hello. Yes, sir.
Yes, we can continue with my talk, or we can discuss also if there are any questions.
I think this is a basic talk, and the questions may be more pertaining to this. So, could you see some questions, or shall I read all
Yes.
from the beginning?
No, I looked at some questions and I also replied to the some questions which I could.
Okay.
Uh,
So, in that case, I think it is better that you can have a look which questions are left out.
Yes. So how can a hole be antiparticle of an electron, as you mentioned? That is the next question that I can answer. So antiparticle in the sense you take one, so you take one particle and antiparticle and you fuse them together, then there is nothing actually. That is what is the meaning of antiparticle. Now there is, let's say, an electron and there is a hole. What is a hole? So let me draw here. Uh, so what is Fermi C? Let us start with that. Fermi C is, let's say, we take p square by 2m kind of Hamiltonian. I'm audible, right? This is a p square by 2m Hamiltonian or the p square by 2m dispersion. So now this is the Fermi energy. Okay. So the Fermi energy, this is EF, let us say. Now all the electrons till the Fermi energy are filled up, and all the states above this Fermi energy, they are empty. Okay, that is what Fermi C means. Now the next question we have is, what is an electron, what is a hole? So electron here is on top of this Fermi C. If I have an electron, okay, so that is above Fermi level. If I have an electron, that is an electron. Okay, this is electron. And what is hole? Hole is absence of an electron below the Fermi energy. So let us say one electron somewhere here, this is absent, let us say. I am marking the absent electron by green patch here. I hope you can see this small green patch. So this is hole. Okay, so now in a system, let's say there is an electron and a hole. Now you bring these two things together. Then electron, what will happen to the electron? This electron can go into this empty state here. Only one electron can be filled here. You remember that? And there is no electron here actually in the green patch. So this electron which is present above the Fermi energy, that can go into this green hole region, and so there is no hole or neither electron nor hole now. There is only simply Fermi C as a result. So that is how you can see that electrons and holes are antiparticle of one another. Okay. So annihilation operator, please elaborate on annihilation operator. Okay. So basically, as I said, on a lattice, let us take a lattice. It is simple to tell these things in a lattice. You can also tell it in continuum. Let's say lattice means you have real sites actually, n equal to 1, 2, 3, 4 like this, or 0, 1, 2, 3 on one side, -1, -2, -3. This is just labeling of these sites. Now, at every site, you can put, let's say, the spin of the electron, let's say we'll fix at half spin. Now, you can put only one electron at every site. Let's say this is an empty site, like this is a vacuum kind of thing. There is no electron anywhere. Now, creation operator, you act on site, let us say 1. Okay, you take this empty state, vacuum state, and you take creation operator, C dagger 1, acting on vacuum state. This will give you ket1, which is actually, which means that there is one electron in the at site 1. Okay, so this is ket1. Like this, you can have many particle states also. Like for example, ket1, ket3, ket5, ket1, 2, 3, 1, 3, 5. This is a 3 particle state. This means that there is one electron at site 1, one electron at site 3, one electron at site 5. Now you take this kind of state and now you operate this by annihilation operator or destruction operator. What does that mean? You take this 135 and you operate this with a destruction operator, that is, let us say C3. At site 3 I am destructing or annihilating an electron. What this will give? This will simply give ket15, which means, so which basically an electron which is present at site 3 is destroyed. That is what it means. So this is just a mathematical thing, okay? Annihilation operator, creation operator, but it helps to write down a Hamiltonian in a lattice model or a continuum model. This is called second quantized language. Okay, this is second quantization. This is very much used in quantum field theory. I am telling you in a very simple way how it can be used in condensed matter physics. Any other question? Okay, in that case, shall I move to my next talk on this altermagnets?
Yes, sir. Yes, sir. Please.
Okay, thank you.
Thanks.
Okay, so I'll tell you what altermagnets are, and also I'll tell you about some of the work that I have done in the context of altermagnets. So cross-sectional reflection I have already told you, but I'll kind of go through it quickly again. And altermagnets can be used to study this or enhance this phenomenon of cross-sectional reflection. Okay. So the nature of electron transport, that is the quantum mechanics that we all know, and it can, in principle, it can be either ballistic or diffusive depending on the length scales that are involved. Let's say L is the sample dimension. Then there is something called mean free path, LM. That is basically the separation between two successive scatterings. Okay, so that is mean free path, and there is something called phase relaxation length, which is very important. So what does this phase relaxation length mean? When an electron travels, there is a phase associated with the electron wave function, right? So this phase, if it preserves the phase along about certain length, that length is called phase relaxation length. Above this phase relaxation length, the phase of an electron, that is actually lost. Okay, so our discussion will be in the ballistic regime, and it will be in the phase coherent regime. If it's in the phase coherent regime, or if then you can actually use principles of quantum mechanics. Otherwise, you will have to use other principles actually. Okay, so and to tell you the order of magnitude of this phase coherence length, it's of the order of micrometers in the realistic samples in the lab. So normal metals, what are normal metals? I told you actually it's basically p square by 2m is the kind of Hamiltonian for normal metals in continuum, and this can actually be mapped to the lattice model also. I told you how it is possible, and in this we will consider zero energy as the Fermi energy. Okay, so at zero temperature, all the states below zero energy are filled, and all the states above zero energy are empty. And that is the reason why I have a mu here in the Hamiltonian that is there in blue, that is written in blue. And what is M? It's the effective mass of electrons. Mu is like the chemical potential or the Fermi energy. Okay, so there is one important result in physics, that is even when there is electron repulsion, okay, in 2 or 3 dimensions, there is something called Fermi liquid theory, which guarantees that you can treat the system by free particle Hamiltonian. That is, there are something called quasi-particles, which are like particles, the effective particles that are responsible for the dynamics. They are like electrons, though they are not exactly electrons. They are electrons dressed with holes sometimes. Okay, so okay, so I'll give you an outline of scattering theory. This is like very simple quantum mechanics. So you have a quantum device in the middle, and on the two sides you have two reservoirs, mu L and mu R. These are the chemical potentials on the two sides. So basically, you can send an electron from the left. There is some reflection probability and there's some transmission probability. So you can write the wave function like this. I have written e power ikx plus rk e power minus ikx on the left side and tk power ikx on the right side. When you match the boundary conditions, you find rk and tk. And after that, the conductance is given by E square by H into mod Tk square, which is actually transmission probability. This mod Tk square that I have, that is the transmission probability. Okay, so E square by H, that's the maximum conductance per spin that is possible in a normal metallic one-dimensional quantum channel. This is due to Landover and Buttiker. So this is famously called Landover formalism or Landover-Buttiker formalism. Okay, so superconductors. So these are basically these things. So it was discovered in 1911 when mercury was cooled below 4.2 Kelvin by this Kemmerling-Onnes, and it was shown that it shows zero resistance to the current flow. Then Meissner effect, that is that if you put a magnetic field to the superconductors, they repel the magnetic field. That is called Meissner effect. These are the key properties of a superconductor. In 1957, the theory for superconductors came that is called Bardeen-Cooper-Schiffer theory. So these people have won Nobel Prize for this theory. And what is this theory? This theory basically says that electrons near the Fermi sea, they pair up due to phonon-mediated attractive interaction. And these Cooper pairs, these paired electrons, they are responsible for superconductivity. That is this theory. I am telling you this theory in a nutshell, but there are many finer details of this theory, which you'll have to kind of read up and learn more physics to kind of appreciate those theories. But there are also unconventional superconductors which are not BCS type, but we'll actually study only BCS type superconductors. Okay, so there is this mean field Bogoliubov-Degen Hamiltonian. So you see in this equation one, the first term is basically kinetic energy on the left, and the second term is basically the Cooper pairing term. Okay, because of the second term in the dispersion, electron dispersion, a gap opens up. I had shown you one three-dimensional picture earlier. This is a two-dimensional version of that. So the blue dashed line here, that's the electron band, and the red dashed line is a hole band. This electron band and hole band, they kind of hybridize and give rise to this yellow kind of band, which actually shows a gap. That gap is called superconducting gap. And transport within the superconducting gap, it is not possible by these particles, that either electrons or holes. It's not possible by that. And transport within the superconducting gap, it happens only by what is known as Cooper pairs. Okay, so this Andreev reflection, I told you, you take a normal metal superconductor junction, you send an electron, and the whole reflects. That is Andreev reflection. And cross-Andreev reflection is basically when you couple two normal metals to a superconductor, and you send electron in one channel and you get hole in the other channel. That is cross-Andreev reflection. And there is a question here by Sanjeev Kumar saying how Cooper pair splitting is inverse of cross-Andreev reflection. Okay, I'll answer that. So let me draw the picture, or I have the picture somewhere here. Yeah, so look at this picture here. So there are two normal metals attached to a superconductor here, right? So now let me send an electron. Let me tell you what is cross-Andreev reflection. So cross-Andreev reflection is you take an electron, you send an electron from normal metal, and what happens is this electron that you send in normal metal, it goes down as Cooper pair into the superconductor ground, and when it needs another electron to go as a Cooper pair, so this other electron is picked up from the other normal metal, which means another electron from the other side, it actually comes here, which is below the first. So this looks like a hole has gone into the second normal metal. So that is cross-Andreev reflection. Okay, so I have sent one electron from the left normal metal. A Cooper pair has gone down in the superconductor. It needs two electrons to form Cooper pair. So the second electron is picked from the second normal metal below the Fermi sea. So because below the Fermi sea, the electron is picked up, it looks like a hole on the second normal metal. So it looks like you send an electron in the first normal metal, a hole is transmitted on the second normal metal. That is cross-Andreev reflection. Now you do the time reversal operation on this. Time reversal operation means like the inverse of this. That is, you take a Cooper pair and you take Cooper pair and send this Cooper pair into the two normal metals. Then one electron of the Cooper pair goes to the left normal metal, other electron goes to the right normal metal. That is called Cooper pair splitting. That is why these two are inverse process of one another. Cooper pair splitting and cross-Andreev reflection. Okay. Fine, let me go to my presentation. Okay, so that is but cross-Andreev reflection, there is a problem with cross-Andreev reflection when it comes to experiment. That is because there is a competing phenomenon for cross-Andreev reflection, which is electron tunneling. You send an electron from one normal metal, it can tunnel through the superconductor and end up on the other normal metal that has an electron itself. And the current carried by electron tunneling and cross-sectional reflection, these are exactly opposite in sign because one is electron and the other is hole. In electron tunneling, it's the electron that is going into the second normal metal. In the cross-sectional reflection, it's the hole which is going into the second normal metal. And the charge carried by the electron and hole are opposite. So electron tunneling current is usually much more dominant in magnitude compared to the cross-sectional reflection. So it is difficult to observe signatures of cross-sectional reflection in the experimental setup. So there is this problem of how to enhance cross-sectional reflection and see its signature in an experimental setup. Okay, so that okay. So one of the ways that is used is to use ferromagnets. Instead of normal metals, if you use ferromagnets, if you have, as I said, in a S-way superconductor, that's the standard superconductor actually, S-way superconductor, the Cooper pairs are basically in the singlet state, as I said. So singlet state means what? It is one upspin and one downspin which make up the Cooper pair. So in the Cooper pair, there is one upspin and one downspin. Now, if you connect ferromagnets instead of normal metals, but anti-parallel, like ferromagnet means it is spin polarized electrons. So there is one ferromagnet, let us say, which is like only upspin electrons are there, and in the other ferromagnet there are only downspin electrons. Then when you insert an electron from one normal metal or one ferromagnet, it needs another electron of the opposite spin to form Cooper pair, and that is picked up from the other normal metal or other ferromagnet. That is why you can use ferromagnets in the anti-parallel configuration to enhance cross-sectional reflection. And electron tunneling is suppressed here because you are sending an upspin electron from one normal metal. It is not converted into downspin electron when it goes to the second normal metal. It has to go as an upspin electron. But in the second normal metal, there are no upspin electron states possible. Okay, that's one way of enhancing cross-sectional reflection. But the problem with this way of enhancing cross-sectional reflection is that you need magnetic fields to repolarize these electrons in the ferromagnet. So the question is whether you can do this without the need for applying magnetic field. And the answer is yes, that is by the use of something called alternates. What are alternates? These alternates, these are materials, magnetic materials with zero net spin polarization or zero net magnetization, just like antiferromagnet. Okay, but they have spin polarized band structure, or in other words, they have spin split band structure, and you have momentum dependent spin splitting here. So this is the Hamiltonian in the tight binding model, like minus 2t naught cos kx plus cos ky, that's in the first term, into sigma naught is the identity matrix, minus tj into cos kx minus cos ky into sigma z. So where sigma z is the Pauli spin matrix. So now if you have this kind of Hamiltonian, you basically have elliptical Fermi surface. And here you see the blue elliptical Fermi surface in the middle, that is for upspin electron, and the red dotted line, this is the red elliptical Fermi surface, that is for the downspin electron. And these two Fermi surfaces, they are separated in space. They are not exactly on top of each other. That is what is called spin split. Okay, but the size of this Fermi surface, you see, they are exactly same. They are not different. The only thing is that they are elongated in different directions. Okay, so that is why there is no net spin polarization or net magnetization in altermagnets. But for example, in ferromagnets, that's on the rightmost side, the rightmost figure that you have, that ferromagnet that has net spin polarization, because the Fermi surface for upspin is larger in size compared to the Fermi surface for the downspin. Okay. So there is another way of looking at these altermagnets. You can actually map the electron hole degree of freedom in the superconductors to the two spin species in the magnetic systems. That is another way, but I think this is a little too advanced for the time being, so I'll not go into this another way of looking at this altermagnet. Let us go on to the physical properties of altermagnets. See, ultramagnets, I said, there is no net spin polarization in ultramagnets. Also, in a normal metal, there is no net spin polarization. But the interesting finding is that you take two systems, that is one normal metal and one ultramagnet, and make a junction between the two, and apply a small bias, then there will be a current that flows, right? And this current is spin polarized. What does it mean that the current is spin polarized? It means that upspin current is more compared to the downspin current. That is what it means. And this, see, the interesting point here is that none of the two materials are spin polarized, but still there's a spin polarized current. Okay, that is an interesting property of this alternate. Okay. Whenever you pass a current on ultramagnet, it is accompanied by a spin polarized current. Okay, so that the reference for this is here. Okay, so let us go to the next thing. That is the important point for this talk. That is how to enhance cross-sective reflection using ultramagnet. You can see this figure, right? There is a superconductor with a green patch in the middle, and on the two sides we have two ultramagnets. And these ultramagnets are rotated by 90 degrees with respect to one another. You can see that the blue ellipse on the left and the blue ellipse on the right, they are now rotated by 90 degrees. Right? So now if you take an electron, let us say a downspin electron on the left, and you send a downspin electron from the left, that downspin electron can go as a downspin electron on the right side only if momentum match, that is transverse momentum match. There is a momentum along y direction, ky. And the Fermi surface, they have to match actually. That's an important condition. And that can match, that cannot match here because you see the red ellipse on the left, red ellipse on the right, they are elongated in different directions. But you look at the downspin electron that is sent on from the left, there is an upspin electron with the same size or the same shape of the Fermi surface for the upspin electron. So a downspin electron sent from the left, it can pick up another upspin electron from the right and go as a Cooper pair in the superconductor, which is cross-sectional reflection. So this is the essence of enhancing cross-sectional reflection using ultramagnets. That is what essentially is being done here is that you take two ultramagnets and rotate them by 90 degrees. So there is no magnetic field applied on each here. Okay, and then in the middle you have a, and now you apply a bias from the ultramagnet to the superconductor, and you will get cross-sectional reflection enhanced. Okay, so it's basically about the Fermi surface property. So these are some results. So this is basically the probability of cross-sectional reflection and electron reflection. The red dotted line here, that's the probability of cross-sectional reflection as a function of the bias. And these calculations were done for experimentally relevant parameters. And okay, so to summarize, we have actually seen for this part, we have seen what are ultramagnets and how to enhance cross-sectional reflection using ultramagnets and without a need for an external magnetic field. So this is the reference from which you can read up. So I have some more slides and there is half an hour. So let me go to the Josephson effect. Okay, so using ultramagnets, you can we can actually come up with some very interesting kind of Josephson effect. I'll tell you what Josephson effect is and come to that. So Josephson effect, this was actually discovered by Josephson. This is a very nice Physics Today article that you can find on the internet, written by Philip W. Anderson. So this this Josephson, he was a PhD student. He was just 22 years old. He came up with this prediction of Josephson effect. So what is the Josephson effect? So between, let's say you take two superconductors, okay, and make a junction. You put a thin insulator in between two superconductors and make a junction. Then if you apply a phase bias, that is, apply a difference in the phase of the superconductor. See, these Cooper pairs in the superconductor, they are quantum particles. The wave function of a quantum particle that doesn't have only a magnitude, but it also has a phase. Okay, so this phase, let us say, can change. So the phase of the left superconductor is, let's say, phi. That is order parameter, or the pair potential is, let's say, beta or I phi for the left superconductor and delta on the right superconductor. Then a current flows in equilibrium from one superconductor to the other. That is what is Josephson effect, or DC Josephson effect to be precise. And there is a current which depends on the phase, that is called current phase relation. So how to understand this Josephson effect? So let us consider a superconductor, normal metal superconductor junction. In between, in normal metal, this electron and hole, these are good quantum particles in the normal metal. These are eigenstates of a normal metal Hamiltonian. So there is left moving electron and right moving hole. So this carries a net current towards left side. And on the right side, I have right moving electron, left moving hole. That carries a net current to the right side. And when there is a superconducting phase bias, the weights of these two sets of processes is different. That is left moving electron, right moving hole, and right moving electron, left moving hole. These two sets of processes carry different weights. That is the reason for this Josephson effect. Okay. Now, this Josephson diode effect, that's a very interesting effect. So usually there is something called critical current. What is critical current? There is dependence of Josephson current on the phase difference, right? So in this curve, there is a maximum and minimum. So the maximum is called critical current in the forward direction, IC plus, and minimum is called critical current in the backward direction, IC minus. Okay. So that is the thing. And typically IC plus is positive and IC minus is negative. So diode effect is when these two magnitudes are different. That is, IC plus is not equal to IC minus with a minus sign. That is called Josephson diode effect. Okay, and this is the Josephson diode effect coefficient, definition of this coefficient. And if the system is invariant under inversion or time reversal symmetries, this Josephson effect does not appear. Okay, so there is some question I see. I'll take that question towards the end of this talk. Okay, there is something called band asymmetric metals where this Josephson diode effect appears. I'll not really go into this, but I'll just go into what is called planar Hall effect. I think I told you about planar Hall effect. Basically, planar Hall effect is that in a spin orbit coupled two-dimensional electron gas, if you apply an in-plane magnetic field, there's a transverse voltage that develops. That is called planar Hall effect. Okay, so Josephson Hall effect and transverse Josephson diode effect. So what is this? So basically you take a lattice like this. That is, there you take four superconductors like this blue patches here, blue lattices. These are actually superconductors. In the middle you have spin orbit coupled region, or you can also have altermagnets with spin orbit coupling. Now if you have this kind of system, then you look at you apply a phase bias from left to right. There's a superconductor on the left, there's a superconductor on the right. Let's say the phases are phi s by 2 on the left and minus phi s by 2 on the right. And the phases of the top and bottom superconductors, they are 0, let us say. Then when there is no spin orbit coupling or Zeeman field, or when there is no spin orbit coupling and altermagnetism at the center, the currents that flow into the top and the bottom superconductors, that is 0. But when there is both spin orbit coupling and altermagnetism, both are there, then there's a net current that flows to the top and bottom surface, bottom terminals, superconducting terminals, as a response to the phase bias, that is, as a response to the phase difference phi s. Okay, so this is called transverse Josephson diode effect. So it comes to the diode effect. This is called transverse Josephson Hall effect, or Josephson Hall effect to be simple. So basically, you are driving a Josephson current in the longitudinal direction, and that will also result in the Josephson current in a transverse direction. That is Josephson Hall effect. Okay, and now you look at this Josephson current, that is Jy versus phi s, and you see that the maximum and minimum, they are not equal in magnitude. That is what is called Josephson diode effect. Transverse Josephson diode effect. Okay, the reason for this is again the Fermi surface asymmetry. When you have altermagnetism and spin orbit coupling, the Fermi surface looks like this, for example. And you see the top and the bottom. So the top point is like y is 0.308, bottom is minus 0.284 for this Fermi surface. Correct. So the ky and minus ky, they don't come in pairs here in the Fermi surface. So that's the reason for this transverse Josephson diode effect. And this is diode effect coefficient that is plotted here versus the phi. Okay, so this is in the Z1 field plus spin orbit coupling, and the same thing happens in altermagnets also. If you have altermagnets plus spin orbit coupling, and this is the Fermi surface. This is the current phase relation here on the top, Jy versus phi s, the superconducting phase bias. And this is the Fermi surface of the altermagnet, that is ABC, the lower left figure. Okay, and these are diode effect coefficients. I am showing this. Okay, and to summarize this transverse Josephson diode effect, this diode effect can appear in normal metal also, but in superconductor that's even more interesting. That is when the band is asymmetric, you can get this. And in superconductor, normal metal superconductor junctions, the transverse current appear when the normal metal region in between has spin orbit coupling and Z1 field, or spin orbit coupling and altermagnetism. And the Josephson diode effect, it shows up in transverse currents and can be measured by an experimental setup in a 4-terminal setup. In this transverse Josephson diode effect, it shows up in altermagnets along with spin orbit coupling. That is the message that I wanted to tell you in this second part of my talk, and thank you for your attention. I'll take some questions. So let me go to the question that is posed there in the chat box. In absence of an external magnetic field and with zero magnetization, what is the physical mechanism that leads to spin splitting in altermagnets? Please explain. Okay, let me explain what is this thing, spin splitting. So this RuO2, that is a candidate material for altermagnet. And in this, there are two kind of Ru atoms. Okay, and the two atoms, their environment of these orbitals, they are like that. So the blue atom has the upspin orbital which is elongated along x direction. You can see that here, right? And the red Ru atom, that has downspin electron orbital which is elongated along y direction. So what this results in is that the hopping integral or the hopping amplitude along x and y direction, they are different for different spins. Okay, so to tell you in other words, so for electrons, so let us take a square lattice. So let us take a square lattice. I will choose magenta color for upspin electrons. So upspin electrons, they find it easy to move along the x direction. Hopping along x direction is easy for upspin electrons. Okay, this is easy, and difficult along y direction, hopping electrons. That is because of the structure of those orbitals. I showed you that, right? So this is for the upspin electrons, but for the downspin electron, the orbitals are actually rotated by 90 degree. So now for the downspin electrons, to hop along y direction is easy, but to hop along x direction is difficult. That is what, and this is an intrinsic property of this material. There is no magnetic field required. Okay, so this is an intrinsic property of this material. That is why even with zero net magnetization, altermagnets have this thing called spin splitting. In other words, let us go to the free electron theory kind of model that we wrote down. Okay, so in free electron theory, what did I write? I wrote p square by 2m, right? So in 2 dimensions, let us take. So the Hamiltonian, I can write it as px square divided by 2mx plus py square divided by 2my, where mx and my are different. They are not equal. Okay. So that means effective mass along x direction and effective mass along y direction, they are different. This is for one kind of electron. There is upspin electron like this, let us say. Okay. And for downspin electron, let us say, for downspin electrons, H is equal to px square divided by 2my plus py square divided by 2mx for downspin electron, let us say. That is, effective masses are different in the different directions even for downspin electrons, but the role of mx and my, they are interchanged compared to the upspin electron. Okay, this is how we can write the Hamiltonian for the two spin. Okay, this is the reason for the Fermi surface, which is elongated along x direction and along y direction in different way. Okay, the elliptical Fermi surface, which are elongated in different directions for the. Any further questions?
I think there are no further queries. Dear participants, if there is any doubt, please write in the chat box.
These ultramagnets are new class of materials which have come up since about 2022. Okay, now there are a lot of theory and experimental work that is going on in that area of ultramagnets. So every day, some or the other paper keeps coming on ultramagnet. If you look up this archive.
Okay, sir. Just a general uh, curiosity.
Yes.
How these altermagnets can be useful in quantum technologies, specifically in any area that they can be used?
Yeah, that's a very good question. So one thing, as I said, this Cooper pair splitting and all this kind of things, you can use that, this ultramagnet. That is one thing. And the important property of ultramagnet, which makes it distinct compared to the ferromagnets, for example, is that you don't need to apply any magnetic field to get this kind of band structure. That's the basic physics. Okay, so taking use of this basic physics, one can come up with technological applications. So one kind of application that people can think of is something called spin valve. Okay, that is, what is spin valve? Depending on the spin orientation of the two ferromagnets, you can control the electrical current in a certain material. That is, if the two ferromagnets are both up, the current is large. One is up, one is down, the current is very small. So this is called something called spin valve. This is very much used in using ferromagnets already. But the same thing can be designed using altermagnets. But the interesting advantage, the interesting property is that with altermagnet you don't need to apply magnetic field, but in ferromagnets you need to apply magnetic field, and that is the technological advantage. So spin valve is one application. So there are many more applications, and there are many new effects that you can find on this altermagnetic field. The splitting the bands. Any other question? Let me look at this. Okay, so there are a lot of questions from the chat box. Let me take this one by one. Let me go to the bottom first. Is it possible to use superconductor as a radiating element in antenna design, because antenna structure is made of substrate with top and bottom conductor part, electron flows in the conductor plus? See, yeah, give me suggestion. Okay, so this is a very ambitious idea, because these superconductors that we know of, they you need to go at very low temperatures. In antenna, how will you maintain this very low temperature? That is very difficult. So I think with the present technology, this may not be possible. But if you get something called room temperature superconductor, this may be possible. That is the answer to Dr. Anandi Meena. And then applications of ultramagnet. Okay, I have told you briefly. In absence of extramagnetic field and zero magnetization, what are the physical mechanisms? So that I have answered anyway. Okay. Any other question?
I don't see any other questions, sir.
Okay, okay. Thank you.
So possibly they may write to you later on, as
Yeah,
and
sure.
when they have some query.
Sure,
So
sure. Yes.
yeah,
Yeah.
it was really nice actually, and I'm really thankful for you for accepting our invitation and covering these topics.
Okay, sir. Okay. Thank you very much.
Yes, sir. Yes, sir.
Okay.
So thank you once again, sir. Thank you so much.
Okay. Okay.
And we can stop the session now.
Okay.
Okay, sir.
Thank you.
Thank you, sir.